manpower is required to go ahead with this technology. So various renewable energy, renewable sources of energy are solar energy, wind energy, wave energy, electrochemical energy, geothermal energy, etc. Out of which mostly our country we can concentrate on solar energy and wind energy. And in Kerala, mostly we have only solar energy, only some small parts only we have wind energy. So most of our concentration will be on solar energy. In future, you will be seeing smart homes. Smart homes means they will not need any power from the grid. It will be self-powered. So this is a Tesla powered smart home. You can see the solar panels as a roof. So they will provide enough energy for use inside the home. What you see are not walls. These walls are basically energy storage devices. So the walls will be storing energy. The roof will be capturing energy. And this energy you can use for lighting and all other applications. Like you can see a car, electric car being charged from this smart home. So these types of smart homes will be coming soon. This is another news article, Tesla Model S long range, 603 kilometers in a single charge. So the cost is the only problem. This is a news article dated 30th December 2019. So in one single charging, you can go about 603 kilometers. So you can see this news, another news article quoting Bill Gates. Bill Gates thinks that electric vehicles are the future of automobile industry, but high price is a problem. So this is a news article dated February 15, 2020. So Bill Gates thinks that electrical vehicle will revolutionize our roads. So as you see the Fifth Avenue, after maybe 5 years, all our roads will be flooded with electrical vehicles. All the petrol and diesel vehicles will be out of the roads. Then again, when we talk about electrical vehicles, these electrical vehicles need to be charged. If you are charging the electrical vehicles from the grid, and if the grid is powered by using a thermal power plant, then the energy is not clean. So you need to charge your electrical vehicles from either solar or wind or any other renewable source of energy. So clean disruption in transportation, that will be soon seen. Even you can see now renewable energy solar charging stations are coming up. Even I saw one in Cochin and I saw one in Calicut. Why we should go for an electrical vehicle? If you see the number of parts in a petrol car, there are more than 2,000 plus parts. And when the number of parts increases, obviously the maintenance also will be high. Whereas if you look an electric vehicle, there are only 18 moving parts, and hence the maintenance will be very, very cheap. And also later, even though the electric vehicles are costly now, later I am sure the price of electric cars will be slashed by at least 1/10. This is a charging station from China. You can see dozens of cars being charged simultaneously. Soon you will see such charging stations in Cochin and major cities. This is a news article dated August 29, 2019. So Tata Power is going to set up 500 electric vehicle charging stations by 2020. So a lot of development, a lot of charging stations will be soon coming all over India. In all the major cities, it's already there. It will be coming to villages also soon. We are set, Rajagiri School of Engineering and Technology, we had set up a solar power charging station. The specifications are given here, and any electric car or auto can drive in and charge, and freely they can charge their vehicle and go out. So this project is done by our students. You can see an electric rickshaw. Again, that electric rickshaw is also under one of our mechanical students project. So the auto rickshaw is being charged by using our charging station. Now, solar energy is another area of disruption. And this is a news from the Ministry of New and Renewable Energy. We had attained a record low solar tariff of 2.44 rupees per unit. So 1 unit of energy, that is 1 kilowatt hour, we achieved, or we can produce for just 2.44 rupees using solar. And the same thing using wind also. So we were able to produce wind energy also for a tariff of rupees 2.44 per unit. If you see this picture on the left, you will see the development in windmills. In 2000, the height of windmill used to be around 64 meters, producing around 1.6 megawatt, a single unit. By 2005, we started producing 3 megawatt. The height of the windmill increased to 80 meters. By 2015, or right now, we are producing around 4 megawatt from a single unit, and the height is about 90 meter, almost the height of the Statue of Liberty. And in another 5-6 years, we will be having a single unit producing around 11 megawatt. The height will be 125 meters, which is more than the height of the Washington Monument. Its radius itself is 190 meters sweep area. So you can see a single windmill in the near future. Commercially, I think commercially it will be available by 2021, this year. One single windmill producing 11 megawatt. So that's a very high disruption. So our dream is to go for 100% solar by 2030. So a lot of solar installations are coming, and by 2030, we expect all countries to move towards solar. Now, countries which are leading the shift to 100% renewable energy, you can see the first position Sweden, second is Costa Rica, third Nicaragua, and so on. The 11th position is Kenya. I have highlighted Kenya because Kenya is an African country. We consider African countries are economically backward or poor countries, and still Kenya is going for 100% renewable energy, whereas you cannot see India in this list. So India also is also on the way. We are producing around 81 gigawatt now by using renewable energy, and by 2022, we will achieve 175 gigawatt. So we have discussed 12 disruptive technologies, and out of which I have highlighted few of them, which are more related to electrical or engineering. Other things like medical innovations I have not highlighted. So I strongly recommend that by your students, by the end of the 8th semester, they should have some certifications on these disruptive technologies like AI, IoT, blockchain, robotics. If they have some certification in these areas, they will be well placed. So 100%, around 139 countries will go for 100% renewable energy by 2050, and this will produce a lot of jobs. You can see at the bottom, and also 27 million people will also lose jobs also. So 52 million jobs will be created, and almost 27 million jobs will be lost. Those people who are losing their job, mostly they will be working in the area of petrol or diesel. So we should make our students having skills in these areas, renewable energy. This is a very promising area. So this is another news article dated 22nd July 2020. Odisha banks on green energy through floating solar parks. So you can see 2200 megawatt solar and 500 megawatt non-solar renewable projects by 2022. So one of the major projects is coming up in Orissa. Sadly, Kerala lags behind proper using of renewable energy, which is basically solar. We have solar. This is another project already installed. Do you know what is this? Can anybody tell me what is this? Anybody knows about what is this project? I'll give you a hint. This is in Kerala. I think that is sufficient hint to find out. Okay. India's largest floating solar power plant opens in Kerala. This is a news article dated 5th December 2017, and this is in Wayanad. So 500 kilowatt peak solar plant by KSEB. It is floating in around 1.25 acres of water. There are 1,938 solar panels which have been installed on 18 ferro cement floaters with hollow inside. So this is one of the major projects in Wayanad district, floating solar power plant by KSEB, even though KSEB claims the actual brain behind this is by 3 students of NIT Calicut. This is their startup activity. The first part is over, which is disruptive technology. So now we will move towards the growing energy needs. This is a news article which says the solar PV is becoming the new king of electricity. So you can see the data 2009 to 2019 in gray color, and 19 to 2040 in blue and green color. Okay, so just to see this is taken by from the website of IEA. You can click on this site and you can get this information. You can see that the coal will be almost, the usage of coal will be almost become zero by 2019. And the usage of coal, gas also is decreasing, where other low carbon wind and solar, you can see it will almost touch 8,000 terawatt hour by 2040. So a lot of solar and a lot of wind energy will be used in the coming next 20 years. Or basically we will almost delete all our, almost get rid of all our thermal power stations and nuclear power stations. This is another graph showing the rising need of energy. By 2035, our energy need will almost double. So this is a very, very serious issue. So when the energy need is doubling, you have to add that much generation. Okay, so our generation capability should be doubled by 2035. Let us go through some data from the website of National Power Portal, npp.go.in. So we will get very interesting data from this National Power Portal. So if you see the statistics, what you are seeing here is all India installed capacity in megawatt of power stations. So let us see the grand total. What you see here, the installed capacity all over India is 3,79,130 megawatts, or I would like to call it in gigawatts divided by 1,000. So around 379 gigawatts. All over India, the installed capacity is 379 gigawatt, or roughly 380 gigawatts we can say, out of which 92.9 gigawatt is renewable energy. So over the next 10 years, we should make this figure 92.9 gigawatt should be increasing to 400 or even more. So that is our prediction. So out of 379.1 gigawatt, around 92.9 gigawatt is renewable energy. Okay, and that renewable energy, it comes from small hydro, wind, biogas, solar, etc. All put together, we have around 92.9 gigawatts. So now remember this figure, the total generation all over India, or the total installed capacity is 379.1. Now coming to the next slide. Out of this 379.1, just to see the last column only, the Western grid contributes the maximum, which is around 135.3 gigawatt, followed by Southern grid, including Kerala. So we produce around 107.5 gigawatts. And the Northern grid, the contribution is 88.7 gigawatts. Eastern is around 42.4 gigawatts. Northeastern is around 4.9 gigawatt. And all over India is 379.1. So the major contributors to the national grid is by the Western grid, 135.3 gigawatts. And next is the Southern grid, which is 107.5 gigawatts. Now you remember the number 107.5. Who is contributing to this 107.5? Tamil Nadu is contributing around 33.9. Andhra is 26.8. Karnataka is 29.4. Telangana is 14.7. 0.0, and Kerala is just contributing 3.1 gigawatt. What a shame. Out of the 107, the total all over India, it is 379.1, out of which the southern grid is contributing 107.5. And out of 107.5, the contribution of Kerala is just 3.1 gigawatt. And our KCB claims that they have excess energy, they are creating more than our needs, blah, 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 which is totally false. Our contribution is just 3.1 gigawatts. This is the real fact from the NPP portal. And let us see the power exchanges. Why we should see the power exchanges? Because we are generating, our generating capacity is around 3.1 gigawatt, whereas our demand is much higher than this. So when the demand is higher than the generation, definitely there will be power cut. And why there is no power cut in Kerala right now? So the left government claims that after they come, the power cut has vanished. This is another lie. The power cut is not there because in 2013, southern grid was connected with the national grid. So our Kerala is connected to the national grid, or I can say all the grids are connected together. What is the advantage? The advantage is we can buy from other grids, or we can even sell from other grids. How we can buy and sell energy? So like the Bombay Stock Exchange, we have the power exchanges in the world. So these are the names of power exchanges in different countries: Australia, Belgium, France, Germany, Hungary. India, the power exchange is IEX, Indian Energy Exchange, and PXIL, Power Exchange India Limited. If you go to the website of these power exchanges, you can see the price of electricity right now, and you can buy at that price, or you can bid it for tomorrow. This is a second page of power exchanges across the world. This is the website of IEX. You can just type www.iexindia.com and you can see the power price, current power price. Remember, the price of energy keeps changing every 15 minutes. So what you see just now will not be after 15 minutes. So this is another website, PXIL. You can see this website also for the energy price just now. This is the price of energy which I took yesterday, 7th April 2021, 6 o'clock, between 6 p.m. and 6:15 p.m. This I got it from vidutpravah.in. You can see the price is 3.47 rupees per unit all over India, everywhere. At that particular point of time, you can buy electricity or you can buy energy at the rate of 3.47. Wherever there is excess, they will sell it. We can see the price from the www.vidutpravah.in. Let us see the price right now. It takes a long time to load. I don't know why. Maybe the network is slow. Okay, let it load. I will continue my lecture. Okay, so 3.47 rupees per unit was the price yesterday around 6 p.m. And right now, if you see it, the price may be less or it may be more. Most of the time, in the morning time, the price will be less. By when the load increases, the price will be high. Okay, so moving to the next slide, you can see the state of Kerala. So yesterday, the current demand was 3475. Remember, our generation was 3.1 only. So our demand was higher than our generation. So the power purchased from exchange is 75 megawatt yesterday 6 p.m. and we were purchasing at the rate of 3.47 rupees per unit. And the day before, we were purchasing for 3.06 rupees per unit. So you can see the difference. Day before yesterday, the same time it was 3.06. Yesterday 6 p.m. it was 3.47. Can you tell me how much you pay? 1 unit. How much do you pay? All of you are paying your electricity bills. So I hope you remember how much you pay. What price you pay for 1 unit? Approximately, it keeps changing with the different slabs. Anyone? No idea? Okay. Approximately, we are paying from 6 to 7 rupees. So you can see what KCB is doing is they are buying for around 3.47 rupees and they are trading energy for around 7 rupees. So each unit consumed, KCB will get around more than 3.5 rupees. So this is why KCB is now running on profit. Our southern grid was connected with the national grid in 2013. So after 2013, KCB started running in profit just because they started trading electricity. Okay, this is just for your information. So the Central Electricity Authority, this is the authority which monitors all this trading and even the construction and generation of different power plants. So you can see this news, 72,705 MVA added up to March 2019 against the annual target. So we are flying ahead of the target. The target was just 62,600 MVA and we achieved 72,705 in March 19. This is just to show you the different tariff, and most of us will come in this tariff which is between 201 to 250. So you will be paying around rupees 7.6 per unit. KCB buy it for 3.5 approximately. So almost more than double they earn from each unit sold to you. This is a consumption forecast. I will skip it. So we are trying to achieve net zero carbon by 2050. That means we have to eliminate all the sources which will contribute towards pollution and rise of environmental temperature. If you see the electric cars, around 2.55 million electric cars are sold right now, 2020, and it is expected to cross 50 million by 2030. The investment on clean electricity right now is around 380 billion, whereas by 2030, it will cross $1.6 trillion. So this means a lot of investment is coming in clean electricity investments. Clean electricity investment means renewable energies. So most of our students, most of the future engineers will be working in these sectors. This is a newspaper article, Hindu, dated October 1, 2019. This is commissioning of Adaman-Kochi Power Highway. So this line was complete, the line construction of Adaman-Kochi enabled buying of electricity, because we cannot buy electricity unless our grid is connected. So this 400 kV line enabled buying of electricity from other grids. This is a table showing the current status of energy consumption. You can see that China tops the list, followed by United States, and then thirdly by India. What you see here is the last but one column, that is the average electrical energy per capita, kilowatt hour per person per year. In India, it is just 1,181, whereas in US, it is almost 12 times. China, it's around 4 times. So our energy consumption per person is very low. As we start moving towards like that of United States, there will be a lot of energy demand. Our installed power capacity is third in the world, which is 379.1 gigawatt. This is a statistics of February 2021. Third is sustainability. So I would like to take a small break, 5 minutes, before moving to this. I think it's okay, man, isn't it? Can I have a break for 5 minutes?
Yeah, sure, sir. No problem.
Okay, thank you. Thank you very much.
Okay, sir.
Okay, good morning. I'm back. So let us
Good morning,
continue. Yeah, good morning. Can I continue?
Sure, sir.
Okay. I hope you can see my PPT.
Yes, sir.
Okay. So the third part is the sustainability. So sustainability is another factor which drive us towards renewable energy and distributed generation. So this also has to be considered. So the existing infrastructure all around the world alone could lead to a temperature rise of 1.65 degrees centigrade. And this rise of 1.65 degrees centigrade will create a lot of climatic changes, and it will result or it will lead towards the melting of the ice in the polar regions, thereby increasing the sea level, and climatic changes will be visible. You will see a lot of cyclones, floods. So the existing existing infrastructure itself will bring a lot of climatic changes and destructions. So somehow we have to reduce the emissions. So you can see the carbon dioxide emissions. It's almost very high, and mostly it is contributed by the power industry. So the power industry has to be completely changed to clean power by using renewable energy. Otherwise, this world will slowly, the world will be in trouble. We have to move towards zero carbon emissions, sustainable transport. I have highlighted the main important things. Zero carbon emissions. So our emissions should be almost zero. Sustainable transport, that is, we should move towards electrical vehicles which are charged from renewable sources of energy. Then health, we should go for energy efficient buildings. We should have sustainable urbanizations and cities. Other points are also important. Reducing the waste, using sustainable material, all other things are also important. But the most important is to cut down the carbon emissions, use sustainable transport, go for energy efficient buildings, and our homes and cities should be more sustainable. This is an example of a sustainable building. This is Hong Kong zero carbon building, which produces all the energy it needs and does not produce any carbon emissions. This is another example. Sial is another project which we have in Kerala, in the airport. So our airport, Cochin Airport, is not buying any energy from KCB. It is generating all the energy for its needs, and it is also selling the excess energy to the state electricity board. So with these three introductions, we can now come to the distributed generation. What is distributed generation? From the word itself, you can understand that the generation is distributed. It is not in one generating power plant. It is distributed all over the geographical area. They are small, modular, decentralized, grid connected or off grid energy sources located near the place where the energy is used. That makes it most important. And almost all of them are renewable based sources. So some of this picture will tell you what are the different sources of renewable or distributed generation. Photovoltaic cells, fuel cells, then micro turbines, wind power plants. All this comes under distributed generation. So maybe after 3-4 years, all our every home will have a generation. Every home will produce its own energy. We will be no longer dependent on the state electricity board or the KCB grid. We will be generating, already in my house I have one. I generate around 12 units per day. I consume around 7 units. So around 5 units I sell every day to KCB. It is grid connected. So once in 6 months they call me and give me a small check for the energy which I am selling to them. So this is going to happen in all homes. Every home will be connected to the national grid, or it may not be connected also. You will be generating energy for your needs. Various distributed generation technologies are, the first one is micro turbines. They are small turbines, 25 to 500 kilowatt, and the size is something like that of a refrigerator. The next one is the combustion gas turbines. They are rotary engines and they extract energy from a flow of combustion gases. So they have an upstream compressor coupled to a downstream turbine with a combustion chamber in between. I will not go to the details of it, which is time consuming. The next one is the fuel cells. A fuel cell is somewhat like a normal battery, normal cell. It converts chemical energy of a fuel into electricity and using a pair of redox reactions. The fuel is normally hydrogen and an oxidizing agent, mostly oxygen. They are different from batteries because they need continuous source of fuel and oxygen to sustain the chemical reaction. So fuel cells are being used. This is a news article, Financial Express, 13th March 2018. ISR and Tata Motors together, they developed India's first fuel cell bus. So this is something, a promising technology. The next distributed generation source is the solar energy or photovoltaic cells. All of you know this. The next one is the wind turbines. So this is another source of renewable energy or distributed generation. Then bioenergy and fuels. We can extract energy from biomass, any organic material which has stored sunlight in the form of chemical energy. It may be wood or wood waste, straw, manure, sugarcane, or any byproducts of an agricultural process, or even your kitchen waste. This can be converted into useful biogas, and it can be the waste can be converted into energy. Then combined heat and power system, or we call it CHP. So basically the hot gases which come out of any process, if you can recover the heat and convert it into electricity. So there will be a heat recovering unit, and then we will be able to convert into electricity, useful electricity. Or even you can connect it to the grid. So such a system is called a CHP system. Stirling engines. Stirling engine is a heat engine. As the picture, you can see the picture. The heat source, the energy from the heat is used to make a reciprocating movement, which can be coupled to a generator and produce electricity. At the bottom, you can see a solar Stirling engine. You can see a TV dish with a lot of glasses sticked on the surface to concentrate the heat energy to one point. And you can see the Stirling engine installed at the top of the dish. And this Stirling engine can generate a lot of electricity. Our students had done a project on this, and it is still under use. Then marine and hydropower. Hydro energy is the energy captured from moving water. So this is a picture showing a mini hydropower generation, a small hydropower generation. The height of the dam will be very small. Similarly, you can extract energy from waves and tides also. So when a high tide occurs, you can stop, you can close the gates, so creating a head, and as you release the water during low tide, it can be used to rotate the force of water can be used to rotate a turbine, and the turbine can be coupled to a generator. Similarly, the bottom picture, the right bottom picture shows how to extract energy from sea waves also. So the energy stored in the waves can be used to rotate a turbine, and the turbine coupled to a generator can produce electricity. Another source, another distributed generation is the geothermal. So in geothermal also, there is a hot reservoir under the earth. So this hot reservoir, the heat in the hot reservoir is used to create steam and rotate a steam turbine, and this steam turbine will be coupled to a generator and produce electricity. The advantages of distributed generation: the energy produced is clean. It reduces the thermal pollution, reduces transmission and distribution losses, because often these distributed generators are located very near to the loads. Offer fuel diversity, meeting power shortage. If you have a solar power plant at your home, you don't have to depend on the KSEB. If there is a power shortage, your home will be still powered. And finally, these distributed energy resources, and distributed generation, DG. Distributed energy resources include battery also, that's all. If you add DG plus battery is equal to DER, distributed energy resources. Now if you properly connect a group of distributed energy resources, then that is called a microgrid. It is a separate autonomous unit with generation, storage, and load. And this microgrid can be connected to the grid, or it may work as a separate unit. Both are possible. We will see microgrid after 2-3 slides. Now, integration of distributed generation to the grid. This is also very important. One thing you should understand is most of the distributed generation, distributed generators, they are renewable energy sources, and they are intermittent. Intermittent means they are not continuous. It is not available all the time. For example, solar, it is available only when the sun is there. It's not available in the night. So it is intermittent. And also it is not dispatchable. So these are the two drawbacks. Not dispatchable means you cannot increase the energy obtained from a solar plant beyond a limit. It's not like a normal generator. If the load increases, we can increase the generation. That is how you maintain the voltage and frequencies. But this is not possible with renewable energy sources or distributed generations. So we need to connect all these widely distributed renewable energy sources so that if one is not working, another will be supplying. And if all of them are not working, also there will be battery storages. So integrating them to the grid, integrating the renewable energy sources and connecting to the grid also is important, because when we produce excess electricity, excess energy, it can be given to the grid, and when we are unable to generate, we can buy from the grid. So this is a connecting all the sources of renewable energy to the grid is important. Secondly, optimizing the electricity infrastructure replacement investment, because renewable energy sources will support the grid. So the investment the grid has to make will be reduced, greatly reduced, or we can optimize the infrastructure replacement investment. If each and every consumer produces energy for his needs, then the grid stress will be almost zero. The grid will be relaxed of the stress. Less centralized and more consumer interactive. Right now we have generating stations which are centralized. The generating stations are not distributed, they are centralized, and it is the generated energy is transmitted and then distributed to the consumers. The consumer has no role. He has no voice also. He just uses and pay the money. But as you move towards distributed generation, the consumer participation is increased. He is responsible for any maintenance and replacement of the DG located in his place. Also, he will look after them. Otherwise, the transformers and other equipments lying outside, nobody looks after them. We don't care about the transformer maintenance or anything. But if it is your property, you will look after them. So your participation increases, your interaction increases. Facilitate market interaction. This is very important. Right now, if we go for grid connected distributed generation, then all the distribution generation which you have will be connected to the grid. So if you have access, you can give it to KSEB. But right now you cannot give it to other markets. KSEB only you can sell to the KSEB. But at a later point of time, you will be directly connected to the energy markets. So if KCB is not giving you good money, you can give it to some other market. So it will facilitate market interactions. Energy efficiency will be high. As you use distributed generation, the transmission and distribution losses will be greatly reduced because the load is very near the generation. So there is no need for transportation of the energy. So the transmission and distribution losses will be reduced, which will increase the energy efficiency. So now we move towards microgrids. As I told you earlier, it is a cluster of loads, micro sources, operating as a single controllable system, and it provides power to a local area. So once again, a microgrid will have many distributed energy resources, DERs. So DER means distributed generators plus storage devices. There will be loads, and all this will be operating as a single controllable system, and it provides power to that particular local area. A microgrid may be connected to the main grid, or it may not be connected to the main grid. So it is a separate entity. Normally, all microgrids operates connected to the grid through a point of common coupling, and we call it as a PCC with the utility grid. So the point of connection or coupling between the microgrid and the utility grid is called the PCC. This is a complete solution for rural electrification. So rural electrification means providing energy to people living in rural areas, like the Adivasis who live in deep forests, or people who live in deep deserts. So microgrid is the only solution for rural electrification, because it is not possible to take the transmission line to deep into the forests or deep into the deserts. So we can have distributed generators where people are living in the deep forests or in the rural areas and provide them with the energy. So why we need microgrids? They are a reliable source of power. If your home is within a microgrid, you don't have to depend on the KCB. Even if there is a power shortage in the or power blackout in the KCB, your microgrid will be supplying power to you. And when there is any problem with the microgrid, your microgrid is connected to the KCB, so you can buy from KCB also. Operation and investment issues. A microgrid will reduce the government investment in the grid, and operation will be looked after. Operation of a microgrid is taken care by the local people. Resilience. This is one important thing. In the event of any calamity, getting back to normal will be faster with microgrids. You don't have to wait for the KCB staff to come and reconnect. You can yourself reconnect fast. So faster resilience. Green power, because most microgrids use renewable sources of energy. The energy you produced is green. It does not produce any carbon dioxide. Complements the main grid. So whenever there is a shortage in the main grid, a microgrid can supply energy to the grid. So it will be supporting or helping the microgrid, the main grid, or in general we call it complementing the main grid. Improved power quality. The power quality will be improved because the distributed generation is close to you. You are responsible for its operation and control. So definitely the power quality will be better. What is power quality? Power quality is basically keeping the voltages constant, keeping the frequency constant, and maintaining low harmonics. Enhances social well-being. Yes, this is one important point. If you provide energy to people living in rural villages, their social well-being will be enhanced. Their living conditions will be enhanced. When electricity reach in rural villages, it can be used for pumping water. So their water problem also will be solved. And finally, market participation. Microgrid is a group of generators and a group of load and storage devices. So this means a group of people, a section of the society comes together to share their resources. So when each consumer in the microgrid has excess energy, put together, a good amount of energy might be available for selling it to the market. So a microgrid will be able to participate directly in the energy markets. Now let us come to the microgrid configuration. So what you see here is distributed generation. One is solar. The output of a solar DG is a DC voltage, which you should convert into AC if you wish it to connect it to the main grid. Otherwise, you can use DC directly to the loads. The second DG is wind. The output of a wind generator can be AC or DC. If it is DC, it has to be again converted into AC and connected to the common bus. And this bus here shown is AC bus. And thirdly is an energy storage system. It means a battery, which is used to store the excess energy produced by the solar and the wind. So the output of the battery is again DC, which has to be converted into AC inversion and then connected to the common bus. The loads, which may be linear or non-linear or sometimes even unbalanced loads, all these loads in this picture, we have only AC loads. They are connected to the common AC bus, and the common AC bus is connected to the main grid at the point of common coupling through a static transfer switch, STS. So through STS, the grid can be connected or disconnected. Remember, whenever you are connecting the microgrid with the grid, you have to do the synchronization. What is synchronization? Synchronization, we know the three conditions for synchronization, but when it comes to DG, there are 5 conditions. So the voltages should be matching or equal, the frequencies should be equal, the phase should be same, the phase sequence or should be same, the phase angle should be same, and also you should see the harmonic content, because microgrids use a lot of converters, DC AC converters and DC DC converters. It might produce a lot of harmonic which may not be acceptable to the main grid. So the level of harmonics should be within certain limits before you connect it to the main grid. This is a picture of an AC microgrid. The difference between AC microgrid and DC microgrid is just the bus. The bus will be the common bus. If the common bus is AC, we can say that it is an AC microgrid. If the common bus is DC, then we can say it is a DC microgrid. Otherwise, other things are the same. There will be distributed generators, there will be batteries, there will be load. Okay, so generators will be there, load will be there, storage will be there. If the common bus is AC, we call it AC microgrid. And all the loads also will be AC loads. This is a DC microgrid. So DC microgrid means the common bus is DC. And if you want to connect it to the AC grid, you have to convert it into AC. DC to AC conversion has to be done. So an AC microgrid is shown here. You can see various distributed generators. You can see a micro turbine which produces AC and we convert into DC. Wind turbine produces AC converted to DC. Fuel cell produces DC. PV array produce DC. Diesel generator set produce AC, we will convert it into DC. Micro hydro, the output is AC, but we convert it into DC. So whatever be your distributed generator, ultimately you convert everything to DC. Why we convert everything to DC? To store. Okay, so we have a battery storage which is DC. So we convert all the output of each and every distributed generator to DC, and then we connect it to the battery storage. Later we convert this from the battery, we convert, or we say it is inversion, DC to AC, and it is given to the loads. All the loads are AC. So once the DC bus is inverted to AC, it is given to the load, and also it can be interconnected with the utility at the point of common coupling. So one difference you should remember clearly is in AC microgrids, the loads are AC. Next is the DC microgrids, the loads are DC. That's all the difference. The output of each and every distributed generator is converted into DC for the sake of storing it in the batteries. Then whenever we want to connect a load, this DC is converted into AC in an AC microgrid. In a DC microgrid, we directly connect the battery output to the DC load. And to connect it to the grid, this DC has to be inverted. This is just another picture of a DC microgrid. You can see the microgrid central controller has RS485 serial communication with each and every DER, distributed energy sources, whether it is a solar or whether it is a load or whether it is a storage. It also has connections with the grid operator who controls the PCC, point of common coupling. Now, microgrids can be in 3 different modes. It can be grid connected. So when a microgrid is connected to the grid, then we call it grid connected microgrid. So at that time, grid is much bigger than the microgrid. So a microgrid operates as an extension of the utility grid. Power flows from the utility grid and it is up to you whether you use it or not. So it is optional. If you want to use the grid power, you are free, you will be charged. Otherwise, you can use your own generated energy. Sometimes the grid will be disconnected. This may be because of some problem in the grid or some problem in the microgrid. So such a state is called an islanding mode. Okay, the microgrid, grid connected microgrid, when they are disconnected from the grid, we call it as islanding or islanding mode. Third type of microgrid is isolated or standalone microgrid. Such microgrids you will find in remote villages, rural areas, deep inside forests, deep inside deserts, or in general, you will find standalone microgrids in remote locations, and they are not connected to the utility grid. So they operate in an isolated mode. So isolatedly operated microgrid. Now, when a microgrid is grid connected, it behaves as a controllable load or source. It has nothing to do with regulating the voltage at the point of common coupling. Everything is decided by the grid. Grid is the master. Microgrid is the slave. So any regulation of voltage is the responsibility of the grid, not the responsibility of the microgrid. Now, any microgrid should not inject harmonics to the grid. So the harmonics and the DC current should be well below the required levels. Otherwise, the utility grid will disconnect the microgrid. So the primary function of microgrid is to satisfy all its load requirements and contractual obligations with the grid. What do you mean by contractual obligations with the grid? So sometimes a microgrid will sign a contract with the grid, with KSEB, that okay, during daytime we will be giving this much energy to the grid. So there is a contract between the microgrid and the grid. So microgrid is responsible to meet the contractual obligations. Sometimes microgrid will be selling energy to the market also. So that also is very important. So if there is a contract to sell energy to another grid, that also should be supplied by the microgrid. Microgrid should not be disconnected during the time of this energy transfer. Now next, microgrid islanding. A microgrid should disconnect when any abnormal condition occur in the grid. So remember, when a microgrid goes into an islanding mode, it is disconnected from the grid. So the microgrid should take complete responsibility of the operation and load dispatching of the microgrid. So they will be faced with the following issues: voltage and frequency management. So when the microgrid is connected to the grid is responsible for maintaining the voltage and frequency. But when a microgrid is islanded, the microgrid controller is responsible to maintain the voltage and frequency within the microgrid. It also should look after the load dispatching. Load dispatching means there should be a balance between the supply and the demand. In any power system, the demand and the supply should be equal all the time. So if the demand is more, you should pump in more energy so that the supply and demand is equal. So this is called load dispatching. So if the load is more and there is no generation, then we should cut off some of the loads. And this process is called load dispatching. The entire load dispatching of Kerala is done from Ramesheri load dispatching center. They take care of the balance between the generation and the load. Power quality. Power quality means keeping the voltage constant, keeping the frequency constant, keeping the harmonics within acceptable levels. So that also the microgrid should take care. Then micro source issues, especially the protection issues of micro sources. So whenever a microgrid moves into the islanding mode, all the protection issues should be also taken care by the microgrid. And the communication among microgrid components. In any microgrid, there will be micro sources or distributed generators, there will be storage devices, there will be load. These three things will be there. So proper communication between them is also important. This is to balance between the supply and the demand and to keep the power quality. In microgrid, control is achieved by two controllers. One is called the micro source controllers and second one is the central control. So we will see what are the functions of micro source controllers and what are the functions of central controllers. Each micro source or each distributed generator will have one controller. That is called the micro source controller. And the entire grid is controlled by one controller, which is called the central controller. So first we will come to micro source controller. Each and every micro source or energy storage will have one controller, which is called the micro source controller. This controller is responsible to control the voltage profile at the load end and power flow of the micro source independently. So keeping the load profile, voltage profile at the load end is one responsibility of the micro source controller. It also should look after or ensure that each microsource supplies its share in standalone mode. So whenever the microgrid moves into the islanding mode, the central controller will give the dispatching instruction that this microsource should supply this much energy, the other one this much energy, and so on. So that instruction will go to the microsource controller, and the microsource controller should ensure that each microsource supply its share. If they cannot supply that share, then there will be a mismatch in the load and supply. So microsource controllers should ensure that they supply its share whenever the microgrid is in the islanding mode. And then finally, it participates in demand side management, load tracking management, economic generation schedule by controlling the storage devices. These terms we will discuss tomorrow if time permits. What is demand side management, load tracking management, economic generation scheduling, and controlling the storage devices. Secondly, we have another controller which is called the central controller, or we call the microgrid central controller, MGCC or CC. The responsibility of the central controller is overall control, maintain the power quality, and the main thing is provide power dispatch. So how much power is to be supplied by each micro source, that is decided by the microgrid central control. It will also supply voltage set points to all the micro source controllers. And coordinating the protection, that is also the duty of the central controller. It has basically two modules within the central controller. There are two functional modules. One is the EMM, or energy management module. Basically, it looks after the load dispatching. And secondly, the protection coordination module, which looks after the protection of microsources and all other devices within the microgrid. So functional modules of central controller, one is the energy management module. So it provides set points for frequency, voltage, active and reactive power to each microsource controller. So what is the frequency set point? What is the voltage set point? What is the active power requirement? What is the reactive power requirement? All this data is given to the microsource controller by the energy management module of the central controller. Then second module is the protection coordination module, or PCM. So protection coordination to faults in grids. So whenever there is a protection, there is a fault in the grid or a fault in the microgrid, or suddenly the grid is disconnected, that is called loss of grid, LOG. So when the grid is disconnected, all the feeders, everything should be disconnected. Physical disconnection should be done from the grid. And when it is reconnected, we have to resynchronize microgrid to the utility grid. So all these activities comes under the protection coordination module, PCM. Now we come to the interconnection of microgrid. Can we take a 5 minutes break, ma'am?
Okay, sir. Okay, sir.
Just 5 minutes. I have to drink some water. Thank you very much.
Okay, thank you, sir.
Thank you, sir. Thank you.
Okay, welcome back. Can I continue?
Yes, sir. Sure.
Okay, thank you. So after we discussed microgrids, so once again, microgrid is a separate identity of loads, generating units, and storage devices. It is an independent unit which can cater to its load, and it may be connected to the grid or it may not be connected to the grid. So if it is connected to the grid, then power exchange is possible. We can connect it to the power energy markets also. Now, there are certain restrictions regarding the size of microgrids. So if you want to supply a lot of loads, then you should either connect the microgrid to the utility grid, or you should connect different microgrids, and we call it a power park. So you can connect many microgrids together to create a power park and exchange energy between the microgrids. So the interconnection of microgrid, the IEEE has put a maximum capability which should be less than 10 MVA. So you cannot have more than 10 MVA in a single microgrid. So if you want to increase the capacity, then you should have more number of microgrids and connect them together. So several microgrids are essential to supply large load packets. So we call it a power park. So these microgrids are normally connected through a common distribution network. It may be the grid itself or it may be a private one. Both are possible. In interconnected microgrids, each central controller, remember, each microgrid will be having a central controller. So each central controller must execute its control in coordination with the neighboring central controllers. Because when you are interconnecting microgrids, there is a problem of exchanging power. So if one microgrid is exporting energy to another microgrid, then both the central controllers should coordinate, because then only the proper load dispatching within the microgrid will be possible. So interconnected microgrids has greater stability and controllability because the structure is distributed. Each microgrid has to take care of its own load plus the requirements sent by the other nearby microgrids. More redundancy to ensure better supply reliability. So if there is any problem, unexpected problem in a particular microgrid, other microgrid can support, and so there is more redundancy. Power failure will not be, power shortage or power failure can be conveniently avoided. And each individual microgrid has to handle only a limited energy, because handling large amount of energy is a real problem. Here it is restricted to a limited energy. So whenever there is excess or shortage, you can share the resources. Now we will see a case study of a microgrid we have in Kerala. So this microgrid has been established by CDAC. So this is some CDAC's microgrid pilot deployment, and it is supported by ANERT. So there is a off-grid tribal colony near Marayur in the Idukki district. There are about 25 houses and around 100 people live over there. So you have to drive 4 to 5 kilometers off-road. Only four-wheel drive will go there. So transporting anything, you need four-wheel drives or jeeps because there are no proper roads. It's almost 5 kilometer off-road. And this is the microgrid deployment scheme done by CDAC. You can see a battery bank at the bottom on the left side. Then you can see a personal computers, a diesel generator set. So the architecture is a low voltage DC architecture. You can see meters which connects to each and every village houses. And 1 meter is connected to the street lights. And another feeder is connecting to the pump house. There is a sump tank also. And finally, there is a telecom tower, which is solar powered. So within the control room, there is a central monitoring, which will keep monitoring the load and the generation. There are solar PV arrays. We get energy from the solar PV. Whenever there is excess, the energy will be stored in the batteries. But as you all know, the solar energy is intermittent. So during night, we cannot depend on the solar. So we have to depend on the battery bank or the diesel generator set. That is why we provide a diesel generator set, because this cannot be connected to the grid because it is far away. So there is no grid connection. So we have a diesel generator set which will automatically turn on whenever the battery storage goes below certain value. So this is connected. The energy produced is also used to pump water to the sump tank. So drinking water is made available to the people living in this remote village, tribal village. And also the solar energy is used to power the telecom tower. So if there are any issues, it will be directly communicated to the CDAC control station located in the city through the telecommunication tower. These are the details of the microgrid. So 25 kilowatt peak solar PV array, 30 kilowatt indigenously developed power conditioning unit and battery manager, 360 volt 300 ampere hour battery storage, and DC, low voltage DC system is used for street lighting applications and with indigenous technology. Then CDAC has used smart energy meters which they had developed. Indigenously developed 3 kilowatt solar charge controller for telecom tower applications. And there is a water pumping facility. There is a remote monitoring facility through the communication tower. There is a 15 kVA backup diesel generator. Then underground cable power distribution. So these are the microgrid features installed by CDAC at Mahaguru for rural electrification, which has really enhanced the well-being of poor people living in that village. So this is the left side. You will see the control room which they have created. And on the right side, you will see the solar panels before installation and after installation, the two pictures. So this is the first picture is the view of the control room. You can see a lot of battery banks over there. Then second picture, you can see a street light. Third one, a smart meter. Fourth one, a diesel generator. And coming to the next second row, you will see light by burning light, street light, then solar panels, and you can see children and families with their cheerful faces. So this is one project, a microgrid project done by CDAC at Mahaguru. The time is 10:41, so the time given to me is 11:30. I can continue, yes, Miss? Okay. So,
Yes, sir.
So actually, during the last break, I have added a sixth section. Only 5 sections were planned, but I added a sixth section, which is an introduction of smart meters. And the picture of this smart energy meter, which you see now, right now, this is developed by CDAC. This is the smart energy meter developed by CDAC. So we will see smart meters quickly. This meter you might have seen, this is the traditional energy meters, which were almost abandoned maybe 5 years before. This is an almost electromechanical meter. You can see a rotating disc. Even this type of meters are still used in laboratories for experimentation purpose. Otherwise, it is difficult to see this type of meters now. This is the second development of energy meter, which is commonly used nowadays in your homes. This is a digital energy meter. There are no moving parts at all. Everything, every measurement and its calculation, everything is done by digital technology. And from that, we move on to smart energy meters. So we will see what is inside a smart energy meter. So in India, we use electromechanical and slowly we move towards digital energy meters. And these meters, we need a meter reader. A meter reader should go to each and every consumer. So we need a lot of time and a lot of labor. This has to be somehow, we have to eliminate the time taken for reading the meter and we have to reduce the labor. And thirdly, the traditional billing system is inaccurate. The meter reader, many times he will note a wrong reading. It is slow, it is costly, it's not flexible and it's not reliable also. So these are the problems with the traditional billing system which we have right now. So accuracy in billing is highly recommended because this will avoid almost all consumer complaints. The smart energy meter gives real power which is consumed and the billing will be accurate. Real-time monitoring is possible and it is less time consuming and very cost effective. These are the advantages of smart energy meter. Here you can see the top, the conventional metering, and the second one is the smart metering. So in a conventional metering, you will find an energy meter in every consumer premises or every home. And you will find a manual reading. A meter reader will come to your home and he will note down the reading. So the disadvantage is sometimes the home might be closed the meter reader cannot take the reading. So either he has to come again or he will write some reading depending on the past readings. And once the meter reader takes the reading, he goes to the electricity office, then gives this reading to the office. And the process of calculating the bill is mostly manual or maybe sometimes by computer. Also, the meter reader has to face a lot of problems, especially the dogs. This is a real problem. The dogs might attack the meter reader. Now coming to the smart metering, smart meters are connected to every home. Within every home, there will be a home area network. And through the home area network, the smart meters get all the information. And this smart meter, they have a communication channel with the grid, so it can give continuous readings through a gateway, through a NAN or WAN network to a meter data management system. So there is no need for a meter reader to come to the consumer premises. The meter reading will be automatically sent to the meter data management system at periodic intervals of time. And moreover, these smart meters are directly connected to the grid, to the control room. So from the control room, the grid experts or the grid controller can disconnect the smart meter or even partly disconnect the load. So controlling the consumer load is also possible from the grid side, from the KCB side. So this is the development of the old electromechanical meter, then to the smart meter. So from this year onwards, we will be slowly replacing our digital meters to smart meters. What you see now is the functional block diagram of a smart meter. So you can see there are 5 functional blocks. The first one is the signal acquisition, then signal conditioning, then converting the data to digital form, then whatever computations needed to be done, and then finally communicate the information to the control room. So the first part is the signal acquisition. So we need the magnitude and frequency of the voltage and the magnitude and phase displacement of current, power factor, active and reactive power, third harmonic distortion. All these things THD are computed. This is done by the signal acquisition part. Signal conditioning part does addition, subtraction, attenuation, amplification and filtering. And third part is the ADC, which converts the analog signals to the digital signals. So the current and voltage signals which are obtained from the sensors, they are sampled and then they are digitized to be processed by the metering software. Then computations, arithmetic operations on input signals, and you have to prepare data for communication, time stamping of the data. So what time you are sending the data, storage, updating the system, all these are done under the computation part. And finally, the communication part. This may be using the PSTN, or it may be done through the power line carrier communication, cable modems, or by Ethernet. Sometimes the communication is also done by wireless, by using Zigbee infrared or GSM, GPRS, CDMA technologies. This is the functional block diagram. As you see here, the top, the live wire and the neutral wire at one end, and the other end is connected to the load. So the current channel and the voltage channel tap the current and the voltage and pass it to the microprocessor AD7751. This is a typical smart meter. The microcontroller or microprocessor will be different. And LCD display, this will display the energy consumed, and after processing of the signal and time stamping, it goes through the GSM network to the control room. There is a small keyboard to make small changes within the smart meter, like calibration or initial adjustments. So the parameters which are monitored are the number of units consumed in a month, the bill of a month, real power, load on a line, and also last unit it takes. These additional features are also possible: tariff options, tax credits, demand response rates. What is demand response? We will see tomorrow. Smart thermostat. Smart thermostat can be used for turning on and off certain devices connected to the smart meter. For example, if your water heater is connected to the smart meter, you can turn it on and off. Or even the utility can control some of the loads. Then prepaid metering, just like your prepaid mobile phone. After some time, you will see prepaid metering. Okay, you prepay it for 500 rupees, and when that 500 rupees is finished, your electricity will be disconnected. Switching is possible. Then this will make grid monitoring better. Remote connect, disconnect of users. Alignment need not come and physically disconnect the consumer. It can be remotely done. Appliance control and monitoring. This is what I told earlier. Whatever appliances, home appliances you have, which can be monitored and controlled. And also consumer incentives for reduced consumption. That is very important. At a later point of time, we will have different tariffs at different times. So the consumer will be forced to delay his applications to a time when the load is less. The features of this meter is they are highly accurate, real-time operation, they are fully automated. The billing, live billing display, you can see your bill every day. What is the bill till now? You can see it. Okay, and you can even get your bill in a missed call, because your the smart meter and the control room and also the consumer, they are connected each other. So you can just give a missed call and get your bill. High accuracy, low cost, Low cost because the meter reader is get rid of, so we don't have to pay him salaries. Reliable, and no need for a continuous GSM network because this smart meter will be sending signals maybe once in a day. So no, even if there is a disconnection in the GSM network, there is no problem. The customer will be happy and less complaints. Theft and tampering is difficult. Allows flexible tariff and hence better load distribution. That is something very important. Right now we have a fixed tariff. Flexible tariff means whenever there is a high load, they will be charging more. For example, from 7 p.m. to 6 p.m. to maybe 10 p.m. the load is maximum. At that time the charge will be more. During the daytime the charge will be less. So this will force the consumer to change his usage pattern. For example, he will not wash the clothes during the peak time. He will shift his washing to daytime 2 o'clock so that he will save energy. Also from the grid side, their installations will be cheaper. They don't have to install generators for the peak load. The peak load itself will be reduced. Only disadvantage is the billing system fail if there is no GSM network. And also you have to pay for the network usage also. And require fixed GSM number. This is not a disadvantage because most of us have many GSM numbers right now. But anyway, you have to pay for the telecommunication. Before you were paying only for the energy, now you have to pay for the additional facilities which you enjoy. So these are some of the references. It's around 11 o'clock. So I think now I will leave some time for questions, if any. Thank you very much for patiently listening to my lecture. So, madam, can we go for the question feedback section? If anyone has any questions, please welcome.
Hello. Hello.
Yes.
Hello.
Yes.
Okay, sir. Okay, sir. So the next section is Q&A section. So if any queries, you can ask now.
I think there are no queries. In that case, shall we wind up for the day?
Sir, I have a doubt, sir.
Yeah, okay, carry on, please.
Sir, my doubt is about the control of distributed generation.
Okay.
Can the reactive power control alone keep voltage output of DG balanced, sir?
How to control the active and reactive power? Yes, that is your question.
Yes, sir. My question is that alone will control that DG. balance the DG? That's my question.
How reactive power is controlled by the DGs, yes?
Yes, sir. Yes, sir.
Okay. See, active power or reactive power, both are controlled by changing the voltage and frequency settings. Okay.
Okay. Okay.
So, if there is a reactive power or active power requirement, the central controller will direct the micro source controllers to change the voltage and frequency settings.
Okay.
Okay, that's all. So
Okay.
the central controller will direct the micro source controllers to change the voltage and frequency settings. Accordingly, we can pump in more active and reactive power.
Okay, sir. Okay, sir.
I will explain it more clearly tomorrow with figures.
Okay, sir.
Yes, I have put it for tomorrow. Any other questions? I think there are no questions. Can we wind up, ma'am?
Okay, sir. Okay. Thank you, sir, for this wonderful section.
Okay. Thank you very much, all of you. We will see again tomorrow at 9 a.m. tomorrow. Thank you for patiently listening to me. See you again tomorrow. Thank you very much.
Okay. Okay, sir.
Good morning. Good morning, everyone.
Good morning, sir. Good morning. Welcome to day 2 online FDP on distributed generation and smart grids. Once again, I welcome our eminent speaker, Dr. Unnikrishnan BC. Welcome you, sir,
Thank you. Thank you very much.
and all the participants for today's session.
So shall I start or wait for some more time?
Sir, you can start, sir.
Okay. Okay. Good morning, everyone. So let us start the day's activities. Let me present my PPT. So hope you can see the PPT.
Yes, sir.
Okay.
Yes,
So,
sir.
okay. Thank you very much. So today we will be covering the second part, that is the smart grid and all those associated smart substations, etc. So before we go ahead, let us see a quote by Mahatma Gandhi ji. You must be the change you want to see in the world. So today I am planning to cover these 6 sections. The first one is the control functions for micro source controllers. Then AMI, advanced metering infrastructure. Then we will come to smart grid. Then we will discuss intelligent electronic devices, phasor measurement units, VAMs, and we will wind up with smart substations. So let us go to the control functions for micro source controllers. I'm starting this session because Sidhu Miss asked one question yesterday. So that question needs little more clarification. So that is why I start with this section. So you can see a microgrid schematic here. This picture is very clear. You can see D1 and DG2, etc., and so on, DGN. So that you can say there are n number of distributed generators. Each distributed generator has a DC link, because each DC generator will be either connected to a solar panels or windmill or any other distributed generator, and ultimately the output of all these renewable sources of energy will be converted into DC. And that is the point where we call a DC link, because ultimately we have to store the energy in a battery. So whatever be the output of the renewable energy, whether it is AC or DC, it has to be converted into DC. So that is what is shown here as a DC link. Then every DG, or we will call in general a micro source, every micro source you will find a controller. Okay, and this controller receives signals from the central controller. You can see the dotted red lines. So every micro source will receive signals from the central controller. The central controller decides the voltage set points, the current set points, the P demand, the active power demand, the reactive power demand, and the load dispatch instructions. Then you can see all these micro sources or distributed generators are connected to a common AC bus. So this means the DC from the DC link, DC is converted into AC, or basically inverted using a VSI, voltage source inverter. And then all these micro sources are connected to the common AC bus. And each micro source may have a local load. So the one micro source may have a local load. As you can see with the DG, nth DG, you can see a local load. And some micro sources may not have a local load. And the loads are normally connected to the common AC bus. And the main grid or the utility grid is connected to the common AC bus at the PCC, which is the point of common coupling, and through a static transfer switch. And this static transfer switch also is connected to the central controller. So the central controller can give a signal to the static transfer switch and disconnect the microcontroller from the main grid. So the main grid also can disconnect the microgrid. So both are possible. Okay. So this is the general schematic of a microgrid. There will be a lot of micro sources. There will be storage devices. There will be local loads. There will be common loads connected to the AC bus. There will be a central controller connecting all the micro source controllers and also connecting the static transfer switch. So with this knowledge, we can go ahead and see how we can control the P and Q in a micro grid. So built-in control features of a micro source controller. One is the active and reactive power control. This was the question asked yesterday. And second is the voltage control. Then the third one is the storage requirement for fast load tracking. Then how the loads are shared by using PF control. So these things we will discuss now. So a micro source, we can control a micro source and keep the real and reactive power output of the micro source constant. Okay. So this type of control is called a PQ control. So any micro source behaves like a voltage controlled current source. So just to see this picture, you can see a micro source which is connected to a power electronic converter, which means basically it is an inverter. The output of the micro source is connected to an inverter, and the output terminal of the inverter, we will call it bus 1. It has a voltage V and a phase angle delta 1. And bus 2 is the is the microgrid bus or the AC bus. Okay, and between bus 1 and bus 2, there is an inductor or inductive reactance X. Okay, so the microgrid bus, AC bus, the voltage is E angle delta 2. Okay, now this V angle delta 1 and E angle delta 2 will be connected, because this delta 1 minus delta 2 will be the power angle. So the voltage V will be leading the microgrid bus voltage. So delta is given by delta 1 minus delta 2. Delta 1 is the phase angle of V and delta 2 is the phase angle of the microgrid bus voltage E. Now the basic idea of controlling the active power is to control delta. Controlling delta means controlling the frequency. So by changing the frequency, we can control the active power P. Similarly, the reactive power is controlled, reactive power Q is controlled by controlling the voltage. So these are the two basic principles one should remember. Active power is controlled by controlling the frequency. Reactive power is controlled by controlling the voltage. And active power and reactive power are connected with the delta and the voltage by the following equations, which you might have seen in the power system. Okay, so P can be controlled by adjusting delta or frequency, and Q can be adjusted by changing the voltage. Now we will see the feedback system here, by which we can control the P and Q. So here you can see the microgrid, which is at the farmost. I don't know, my pointer is missing, I don't know. Okay, so you can see the microgrid at the right end, and this microgrid voltage, or we call it the terminal voltage, that we will tap the terminal voltage, and that is broken down to the direct and quadrature components, that is represented by VD and VQ. So what we are going to do is the terminal voltage is tapped, and that is converted into the direct and quadrature components, VD and VQ. Now the direct and quadrature components of the output current, that is given by ID star and IQ star. Okay, ID star and IQ star, these are computed from these voltage components and the P and Q requirements, which is represented here by P star and Q star. And this, remember, this P star and Q star, that is the active power requirement, and reactive power requirement is supplied by the central controller. Okay, so central controller will decide what is the active power to be shared by a particular micro source, and what is the reactive power that has to be shared by a particular micro source. So P star and Q star will be sent by the central controller to the micro source controller. Okay, so from P star and Q star and the feedback signal VD and VQ, we will find the direct and quadrature components of the output current, that is ID star and IQ star. Now, if we know ID star and IQ star, ID and IQ we are getting from the output current. So the difference between ID star and ID and also IQ star and IQ is used to drive a PI control, which will produce VD star and VQ star. So VD and VQ is already available. So VD star and VQ star, once we find the difference between these two signals, will drive the inverter, voltage source inverter. So thereby, so whatever be the P and Q demand will be met by the VSI. So this is the basic scheme of meeting the P and Q demand. The same thing is represented in another figure here. And from the PCC, we will take a tapping and we will get the voltage. The P reference and Q reference is supplied by the central controller. So knowing P reference, Q reference and V, we can find the I reference. I again comes from the tapping of the grid bus. From I and I reference, we can actuate the control, and the control signal goes to the pulse width modulation part of the inverter. So thereby controlling the P and Q demands. Now we will understand what is droop control. Okay, so the droop, you can see on the left side, you can see the droop characteristics. The first one is P, and second is V. So basically to meet the P demand, and also we have to adjust the voltage to meet the Q demand. Okay, so the output frequency and the voltage of the inverters follow the droop characteristics as shown in these pictures. Okay, so if we make a small change WP, okay, then the frequency also changes by delta F. So the micro sources will change their output by delta P. You should see the first figure. When the frequency changes by delta F from the nominal values. Okay. So by changing a small frequency, we can adjust delta P. Okay. So a change in reactive power is achieved by changing the frequency slightly. Similarly, the additional demand of Q, reactive power, is achieved by changing the voltage slightly, that is delta V, that you can see from the second figure below, the droop characteristics, the second picture. A small change in delta V will produce a change in delta Q. So basically you should understand that by changing the frequency, we can change the active power. By changing the voltage, you can adjust the reactive power. Now, coming to droop control, as a typical picture is shown here with two micro sources. So you can see here the first picture, micro source 1 and micro source 2. And third one is a storage device. So in a particular micro grid, let us assume there are two micro sources and one storage device. And initially the frequency is F0, which is shown on the y-axis. So whenever there is a active power demand, which is sent from the grid through the central controller to the micro source controller, that will be divided into delta P0, delta P1 and delta P2, and it will be given to various micro sources and storage devices. So you can see from the first picture, to achieve delta P0, the frequency has to be reduced. Similarly, to achieve P1, the frequency has to be reduced. And also to make a change in P2, delta P2, we have to reduce the frequency. So in general, all the the micro source 1, micro source 2 and the storage devices, they will face a new frequency, F new, a reduced frequency, to meet the total requirement. Okay, so the total P requirement is delta P0 source 2. Okay. In a similar way, any additional demand for Q also can be met by reducing the microgrid voltage from the nominal value V0 to a new value V new. Okay. So we should be very careful here. So we are playing with the frequency and the voltage. So the voltage is going down or the frequency is going down. Now there are some limits beyond which you cannot reduce the frequency or reduce the voltage. So there are some maximum limits to which the microgrid can supply the active power and the reactive power. Now we will see why a voltage control is essential in a microgrid. So controlling the voltage is very essential in a microgrid to ensure stability and reliability. Why a microgrid is not stable, we will see here. In any microgrid with a large number of micro sources, reactive power oscillations might happen. These reactive power oscillations will lead to circulating current, and sometimes these circulating currents will exceed the maximum limits of the micro sources, which will lead to the damage of micro sources or tripping some circuit breakers. In a conventional grid, these circulating currents are limited by the large impedances between the two generators. But in a microgrid, the feeders are radial with very small impedances between the sources. So these circulating currents sometimes will become dangerously high. So it may lead to tripping of circuit breakers or even damaging the micro sources. So what can be done? So these circulating currents can be controlled again by using the VQ droop controllers. Okay, so basically we will change the voltage set point to either increase or decrease the Q and thereby reduce the circulating current or making the circuit current zero. Okay, so the controller increases the local voltage set point when the micro source reactive current is dominantly inductive. So this is how we will play around with the circulating currents. So there is a maximum value of the Q reactive power, which is given by the equation Q max is equal to under root of S square minus P square. S is the VAR VA rating and P is the active power. So beyond which the microgrid cannot take care. So there is a maximum value of Q max, and similarly there is a maximum value of P also. So if the microgrid has to supply more than the maximum values, then it has to take some power dispatching decisions. It has to cut off some of the feeders. Now storage devices, that is batteries, are very important in microgrids, because initially when we switch on or connect a microgrid to a main, there will be a lot of power imbalance. Sometimes suddenly some new loads are connected, so there will be a power imbalance. So in a traditional grid, this power balance is taken care of by the large inertia of the generators. But in a micro grid, this has to be taken care by the storage devices. So the storage devices should immediately pump out the required P to take care of the additional loads. So micro source controller should always take care of the storage devices for fast load tracking. So whenever the load suddenly increases, the storage devices should immediately support the microgrid. Another way to share the load is by using PF control. Okay, so again the idea is the same. Whenever there is an additional P requirement, we have to reduce the frequency. That is the whole idea. Okay, so microgrid controllers ensure smooth and automatic changeover from grid connected mode to standalone mode and vice versa. So when we have a microgrid, it has to be connected to the grid and sometimes it has to be islanded. So this changeover, it means a lot of load unbalance or load fluctuations. Okay. So during this transition, when it goes to connected mode or disconnected mode, so each microsource controller will exert a local PF control. Okay, so microsource will not wait for the instruction from the central controller. So microsource will see that, okay, an additional load requirement is coming, so it will automatically reduce the frequency. So this is a local setup. So it means every microsource controller is responsible for the local power balance. Okay. So here you can see how it can be done is just reduce the frequency. Okay, so reduce the frequency of the microgrid and come to a new frequency. But again, remember there is a minimum value of the frequency beyond which we cannot go. Okay. So when the grid is connected to the grid, okay, so the microgrid loads are supplied by the utility grid and also by the microsources. So when the utility supply is suddenly interrupted, the microgrid will switch over to the islanding mode. So when it goes to the islanding mode, the voltage phase angles will keep changing. Okay, whenever there is a disconnection, the voltage phase angle of the microsources will change. Okay, so this will, when the voltage phase angle is changing, means this will reduce or drop the power output of the microsource. So immediately when the power output is dropped, the microcontroller has to balance it locally. So it will change the frequency locally. Okay, it will not wait for any load dispatching instruction from the central controller. Now remember, because of this, the microgrid frequency gets reduced. Okay, so the microsource controller should have a control function to restore the frequency after some time, because we cannot run the microgrid at a lower frequency. So there should be a built-in program that is called a control function, which will bring back the normal rated frequency within few seconds. So with that, we finish first. If there are any questions in this part, I will be happy before going to part 2. If there are any questions, anyone? Okay, we can postpone the questions to last also. So let us see now. No, smart meter is just one part of the advanced metering infrastructure. So advanced metering infrastructure is the complete infrastructure which includes the software, the hardware, the communication channels and all other things which we are going to see now. So AMI stands for Advanced Metering Infrastructure. So this basically, it is an integration of advanced metering technology with communication technology and allow two-way communication between the utility and the customer meter. Okay, so that is the main important part. Yesterday we had seen a smart meter. Smart meter is just a party allows the utility to send signals or to communicate with the smart meter and also contact the utility. Okay, so there is a bi-directional communication channel. Right now, some such structures are not available in Kerala, but soon we will find such systems implemented here also. So the various parts of a AMI, the first part is the smart meter at the user end. Without a smart meter, we cannot implement AMI. Then a smart meter network, because the smart meter, now again, when I say smart meter, it need not be always electric meter. It can be a water meter, it can be a gas meter, or any other meter, which can, okay. Now, smart meter network, this network can be a Zigbee network, it can be a GSM, it can be a broadband over power line, it can be an internet or intranet, it can be Wi-Fi. Then the signal generator unit, which will be situated somewhere outside your home, near your home. So all the smart meters in the nearby area will be sending the data to the meter data concentrator. Then there is a meter data acquisition system. So it will acquire the meter data and then integration of this data with the management system managing the data. So there is a MDMS, meter data management system, and everything has to be integrated with the SCADA. SCADA stands for Supervisory Control and Data Acquisition. And there should be an IT infrastructure for the MDMS. So we should remember that the different parts of an AMI starts with the smart meter, then a network by which we can connect the meter with the meter data concentrator unit. Then we need the hardware communication line, the software meter data acquisition system, meter data management system, and the IT support. So all these things are important, and these things will slowly change the whole scenario. So that is, we are slowly moving towards a smart grid. So you will see later, a smart grid is basically an electric grid, a normal electric grid, plus the communication channel, plus the IT support that we will be seeing maybe after this. So let us see the components of an AMI in little more detail. So you can see the first picture. You can see the meter, and there is a communication network, and there is a router, and then through the router it reaches the meter data management system. That is one way. Another way is there is a neighboring, second picture I am talking, there is a neighborhood area network, or we call it a NAN. So various smart meters will be connected to the NAN, and then the signal reaches the meter concentrator, and through the communication network, it will again DCC router, and through the LAN it can be other some communication which like Zigbee or had earlier. Secondly, the smart meter. Without smart meter, we will not be able to implement the AMI. Okay, so these meters should be supporting a communication interface to connect to the neighborhood area network. Then third one is the meter data concentrator or collector. Okay, so this is responsible for supporting the communication with the meters over the neighborhood area network, and it will collect the meter readings periodically and also generate alarms, and also it will send commands sent by the meter data management systems to the meters and receive the corresponding responses. So MDMS can send signals to the smart meter. It can even control the load. In future, your house, various loads will be categorized into critical load and non-critical load. Critical load means maybe one light in every room and one fan in every room. All other loads like your refrigerator, your washing machine, your electrical pumps, heaters, or all the heavy loads will be connected to a non-critical. They will be considered as not critical, and MDMS can send a signal to the smart meter and disconnect the non-critical loads. So this is very important, and it's good also in one way, because whenever there is a sudden load fluctuation, so suddenly the load increases. So what the load dispatching center can do is either bring more P by turning on new generation. That is one way. But if there is no generation available, then what it can do? What it will do is to cut off some feeders. That is called power cut. So cutting off a feeder means all loads in that particular line will be blacked out. Instead of that, advanced metering infrastructure can send a signal from the MDMS to the smart meter and disconnect the non-priority loads. Critical loads will be there, non-critical loads will be disconnected. So as a consumer, your house will not be blacked out. Essential loads will be still there. So this is good for the consumer and as well as for the utility. And finally, the head end. It is the AMI meter management system. You can see the head end in the second picture. It communicates with the concentrator, meter concentrator, over an IP connection provided by the smart grid. So to implement AMI, we need a smart grid. Without smart grid, we cannot implement all these things. Now, various characteristics of AMI. It is one of the main link between the consumer and the grid. Generation and storage options distributed at consumer locations can be monitored and controlled. This is one of the very important characteristics of AMI. So in the consumer premises, there will be generations, distributed generations, and also some storage devices. This can be monitored by the AMI, and also it can be controlled. So in need, we can even use those distributed generations and the storage, and the grid can pay for it. Thirdly, every consumer is now connected through the internet or through the communication channel with the outside world, so he can actively participate in market. So participating in energy market means it may be buying energy or selling energy. If we have excess energy, we can sell. We need not sell it to KSCB. We can sell it to any other grid or any other needy person. Okay. Similarly, we can buy also. We need not always buy energy from KSCB. It's not possible right now, but at a later point of time, there will be a lot of third-party supplies of energy in your area. For example, in Kochi, the Tata might be supplying power, like in Bombay. Bombay is the entire Reliance may be supplying, KSCB may be supplying. So you can choose be provided to the consumers. Then a solution of the problem diagnosed, and we can find a solution immediately. Then distributed operating model reduces a centralized operating model. It is easy for a terrorist attack, because once the central facility is damaged, the entire city go into a black. But if the model is distributed, then at least many parts of the microgrid will be operated. Part of the OMS, going to details of self-healing, and OMS stands for outage management system. That when there is a sudden power outage, what should be done? This can be accelerated. We will not go to the details of OMS in this particular course. It can also provide a ubiquitous distributed communication infrastructure. That's also important, because this type of MI needs a strong internet connection coming to the internet. You have heard, I will show you the later. You might have heard that case is coming. The reason is very obvious. The words AMI and smart grid. So AMI data improve asset management and operations. This is also very important. If you look at the KSCB all from the meter till the power station, from the power station to the substations, the transmission lines, the transformers all along the way, till your consumer meter, everything belongs to the utility, or everything belongs to KCB. And monitoring all these assets is a big task, especially the transformers, which are located in various parts of our city or in the villages. So asset management is not done meticulously right now. So managing the assets, maintenance of the assets, replacing the assets. When we will replace a transformer? We will replace a transformer when it burns out. One day the transformer will burn, and then suddenly ACB people will wake up, they will come and take it and replace that transformer. So if there is proper maintenance, proper knowledge of the assets, and then our power system will be more reliable. So if there is a communication channel which will monitor the health of each and every asset, which will take care of the repair schedules, then it will be better. So all this is possible. These are possible with IT support and communication channels and IoT devices installed with every asset. Let us see the overview. You can see there are three layers. One is the consumer portal layer, and second is the metering layer, and third is the consumer, or it can be a commercial or industrial consumer. So any customer or any consumer will be having a smart meter, and these meters will be connected to the metering layer. The meters or in offices or industries, they will be connected to the metering layer. Consumers has access to the consumer portal layer. With your login, you can log in and you can see your bill, nothing more. So every consumer will have an access to the consumer portal layer through certain security passwords and username. So even commercial and industrial consumers will have this access. On the other side, the communication is essential for the operations and also for the providing various consumer services. So the communication layer will send signals to the either to the home area network, to various distributed energy resources, or it can send signals to the smart meter also. So what are the benefits of AMI? Why we need AMI? So there are, without any benefits, the consumers will not accept to go for AMI. So the consumer benefits, the consumer will get more, and later we will have dynamic pricing. So the cost of energy will not be constant all the time. The cost will change with time. In the evening time when the load is high, you might have to pay prices about price and services. Manage his consumption fitting to his pocket. That is the consumer benefits. The utility benefits, that's also very important. How the utility is benefited by AMI. Will like to have a load line which is fairly constant. Increases at particular time slots, for example, evening 6 p.m. to night 11 p.m. The energy demand is high because all of us will turn on the lights. But then what is the problem? The problem is the utility has to keep an infrastructure to meet the peak load. And the peak load comes only maybe 2 hours. So out of 24 hours, the peak load comes for only 2 hours. And for that 2 hours, you have to keep your infrastructure. You have to put a lot of investment to procure the infrastructure. So from the utility side, they will like to have a flat demand of load. So how this is possible? It is not possible completely, but yes, it is possible by having a dynamic pricing. Increase the price of energy during peak hours and reduce the price during off peak hours. So what will happen? The consumer will slowly shift his load from the peak hours to the off peak hours. So this is one way of controlling the load curve constant. So this is possible only if we have AMI, communication networks, and billing according to the time of use. Thirdly is the benefit from the society. So improved efficiency in energy delivery and use, and will produce a favorable environmental impact. So environment completely eliminating the pollution and slowly switching to 100% renewable energy. Demand response and innovative energy tariff. This is what I mentioned right now. Demand response means keep a dynamic pricing in order to change the energy utilization pattern of customers in such a way to achieve a flat energy demand curve. Accuracy is another factor because these smart meters are not electromechanical meters, so they are digital meters. They are very accurate, and customers will be more happy because there will not be any confusion and overbilling. What are the challenges? Main challenge is the high cost because you have to bring the infrastructure first, the communication line, IT support, the software, hardware, the smart meter. Who will bear the price for the smart meter? So the customer will say, no, I don't want a smart meter. You put a normal meter. Why I should pay heavily for this? So these are the challenges. Then standardization, interoperability. Interoperability has to be defined. Different companies come up with different meters without any standardization. So in that case, what will be bound to use only one type of meter because there is no interoperability. So you cannot change the meter as you like. So standardization should come in this sector. Then so all these three should be integrated. Right now, KCB has only the electrical setup. They don't have the IT and communication setup along with it. Of course, there is a power line communication between the substations and the generating stations, but no communication support to the consumer, reaching the consumer. Then education is very important. Consumers should be well educated about the need of this AMI. Otherwise, consumers will just reject this idea because it will affect their regulations. So I will take a 6 minutes break. Can I take a break, miss? The time is now around 9:57. Can I take a break, miss? Miss? Good morning. I am back here.
Good morning, sir.
Good morning. Can I continue now?
Yes, sir, sure.
Okay. So we will start the third section, which is the smart grids. So let us understand what is a smart grid and why we need a smart grid. So as this picture says, a smart grid is a grid connecting almost all renewable energy sources. It will connect homes, factories, power plants, offices, storage devices. So it is a network which connects all types of energy resources, storage devices, and loads. So let us go to the next slide. Here you will see a news article dated September 2, 2020. Kerala plans to provide free internet access to 20 lakh families by 2020. So Kerala government through KSEB is planning to provide charging, because once you is the people will accept it at home, then they will not disconnect it. With this internet and the smart meter, the Kerala government will be able to connect every home to a network, so thereby implementing AMI, automatic meter infrastructure. That is number one. And number two, they will be able to set up a smart grid. So what is smart grid? We will come now. All of you are aware about the traditional power grid. So in a traditional power grid, there is a, then what you see is in blue color is the transmission lines. These lines can be 138 kV to 30 kV or even higher. So from the generating, the generated is 11 kV, it will be stepped up to a higher voltage to reduce the transmission losses. And then in the substation, the voltages are stepped down, again back to 11 kV, and again transformers located near the consumer, and where again the output is output of the distribution transformer is normally 3-phase 400 volt or 415 volt. So single phase consumers will be taking 1 phase and neutral, and 3-phase consumers will be connected with all the 3 phases. So if you see a traditional power grid, the power flows in one way. The generation is centralized bulk generation, and it heavily depends on coal and oil. So there is limited automation, limited situational awareness. Consumers have no role in power grid. So now we go into a smart grid. In a smart grid, there will be two-way flow of electricity and information. So if you need a two-way flow of electricity and also information, then you need a communication infrastructure. Without communication infrastructure, you cannot have information flow in both directions. And why there is two-way flow of electricity? Directions. So smart grid is will be connecting more and more devices like the electric vehicles, the renewable systems, which consist of three layers. The first layer is the power and the energy layer. Second is the communication layer, and third is the IT layer. The first layer is already existing, so we have to add the second and third layer. Okay, adding the third and second layer will make the existing traditional grid smart. So the existing is smart just because it doesn't have a communication layer, the IT layer. So if you see this is a conceptual model, reference model of the smart grid. What you see at the bottom is the generation, transmission, distribution, and the customer. These four already we have in a normal grid, traditional grid, and to which three more things are added. One is the service providers. So right now we don't have any service provider. The service provider is only KSEB. Later, large number of consumer service providers will come into play. Then operations, various operations. We will see what are the various operations. Then market will be connected to the energy markets. So all these seven to the grid smart. So this is a detailed figure of the smart grid architecture. So you can see here in each section there are many detailed functions. Okay, so even if you see the service provider, there will be utility providers, third-party providers, and all this has to be connected. All these providers should be connected through the internet to the consumer, to the operations, to the transmission. So various things are there. So each and every part of this architecture has to be dealt in detail. We will not go to that detail in this small time. So only understand that there are 7 parts in this architecture, and each part functions within it. Now, why we need a smart grid? Our traditional electrical grid is already highly stressed. Highly stressed means our grid cannot take more load right now. And because of that, they are prone to frequent failures. So what we have to do is we have to do something to reduce the stress. And that is only possible by making the consumer participate in the generation and distribution of energy. If the consumer starts generating his energy, or at least if he is willing to change his usage pattern so as the peaking of the load can be reduced, of initial investment can be saved. The energy demand is increasing at a very fast rate than the energy supply, because our population is increasing every day. So almost yesterday I told you, in 30 years the energy demand will double. By 2030 the energy demand will be double. So unless we add our energy generation, we will not be able to supply for our needs. So doubling our energy generation is very difficult. So we have to see alternate ways of managing the situation. And also, as the energy no more aware about energy costs, the customers don't want to use energy which comes from thermal power stations. So if there is a choice for the customer or consumer, okay, this energy from Tata comes from thermal power station, this comes from nuclear power station, and a third comes from renewable. Many consumers will opt for renewable energy, even if it is little high price, because they are more concerned and about environmental impacts of other sources of energy. They want to manage energy usage. All this is possible only if they are well connected through a communication channel and proper software support due to energy consumption. So this will lead to a high catastrophe because of the increase in the average global temperature. So that also is. What are the various opportunities of smart grid? Smart grid help interact all the micro sources, various types of renewable energy sources, storage devices, etc. So all this can be interconnected. Interconnection is possible only if there is an electrical line and a communication line. Online power exchange. Online power exchange means you are able from another microgrid or a third party in the open market and sell it. Cheaper power to consumers and better choices. DISCOM stand for distribution companies. So in future there will not be only KCB, there will be many distribution companies. So when there is a competition between two distribution companies or many distribution companies, the consumer will be benefited because they will get better service and they will also get cheaper energy. It is just like our telephone network. We have Vodafone, we have BSNL, we have Reliance and many other companies. So better go for that particular for particular the distributed energy resources are well connected. So we need a smart grid to optimize consumers, promote smart education is one part. To educate the change asset is very KCB will be reduced, thereby our living will be better. What are the challenges? Then nothing can be done. So we need to increase the Adaman Cochin line facilitated in bringing energy from other states and other grids. Similar lines has to be so that manage the city well. Then offshore wind farms. Farm get a lot of energy, but the problem is the space. In Kerala, you cannot find a space on land, but you can find a lot of space in the sea, like floating solar power generations, or if you can have solar installed river and sea. This is a challenge. Then energy devices. With high.
Sir? Sir, voice is breaking, sir. Hello, sir.
A lot of distributed generators are pumping energy to the grid to be developed. The communication infrastructure has to be developed. Just hold a second, 1 minute.
Hello, sir.
The sound is breaking. Is there any problem?
Yes, sir. Voice is breaking, sir. Hello, sir. Am I audible?
At your end or? Yes, you are audible.
Sir, voice is breaking. Little bit breaking, sir.
Shall I continue? Shall I hold for one or log in again?
Sir, can you please log in again?
Okay, I will log in again. Okay.
Okay, thank you, sir.
Okay, Miss, I am back. Is it audible?
Yes, sir. No problem.
Okay, so I will continue. So I have changed the network.
Okay,
Okay, thank you. I will
sir. Thank you.
continue. Okay, thank you. So there are many challenges. One is the increasing the utility grid transmission capacity, installing more wind farms offshore or solar installations offshore, then having storage devices with high energy density, then developing the decentralized architecture and developing the communication infrastructure. These are all challenges. And finally, we have to educate the consumers, because without their acceptance, we just cannot implement it. So these are the various challenges in implementing the smart grid. Yes, also there is a problem of protection and control also, because when the energy starts moving in both directions, the existing protection devices are not sufficient. So we have to go for new methods of protection and control. And the initial cost is very high. So who will bear the initial cost? Either the consumer will bear it, the government, or the utility. Then power quality, because all these renewable energy sources, they use a lot of converters and inverters, which will automatically introduce a lot of harmonics. So a lot of power quality issues will be there. And stability is a major issue. How much renewable energy can be penetrated, or how much the utility grid can allow, what percentage of energy can be allowed to penetrate into the existing utility grid. So that is another question. So there are technical issues, stability issues, which needs to be concerned. It's not like utility grid, you can throw whatever energy you produce, you can just throw into the utility grid. That's not possible, because the utility grid, the feeders are connected to the transformers. If you start pumping in a lot of energy to the secondary of the transformer, the effects are devastating. I mean, we have to study and understand what percentage penetration is possible. So right now, KCB is allowing only around 10 to 15% of penetration. But some countries like Germany and all, they had achieved 80% to 85% penetration. Then we have to have better electrical vehicles, charging electric, because we need to charge electrical vehicles. Then political and economic frameworks and traditions. So these are all challenges or barriers. The political willingness should be there to implement it. And lack of standards, that is also a problem. And lack of regulations also is a problem. So right now you can install solar at your home and you can connect it to the grid. And what are the problems? If the protection problems, and if there is any legal issues, there should be proper regulations. So proper regulations, proper standards, proper legal framework, all this has to be, all this should be there. Then only we will be able to implement a smart grid. So the anticipated benefits, the power, reliability, and quality will be improved. Then the need for a backup power plant will be minimized. We don't need a backup power plant. So the existing electric grid, which is highly stressed, can be used in a better way, or we can enhance the capacity of the existing electric grid by properly managing the load, improving resilience to disruption and being self-healing. So resilience is the ability of the system to restore energy in minimum time. So especially in the event of some calamities like floods or storm, our electrical infrastructure will be badly damaged. So the resilience is really a problem. Especially you have seen in some parts of Kerala like Alapi and all. After the water flooding, there was no electricity for months. So the resilience is poor. The resilience will be better if we have a smart grid, if we have distributed generation, because each and every consumer will start powering up his distributed generator, his home. Expanding deployment of renewables and distributed energy resources. So we have to deploy a lot of renewable energy sources throughout our country, throughout Kerala. And that is possible if each and every one of these is connected to the smart grid. And then automate the maintenance and operation of the grid, reducing greenhouse gas emissions and to provide a clean environment, reduce the dependence of oil, then enabling transition to electrical vehicles. So right now we are using petrol or diesel vehicles, and we have to go for a transition to electrical vehicles, and also provide a lot of choice for the consumer. So these are the anticipated smart grid benefits. We have to wait and see what all these things are possible. This is a comparison of the existing electric grid and the smart grid. Existing electric grid is electromechanical and analog. Smart grids are microprocessor controlled and digital. Electrical grid is reactive. Smart grid is proactive. Electrical grid is prone to failures and blackouts. Right now we have one pricing. Later in smart grid, we will have real-time pricing. Right now in the electric grid, we have no choice or limited consumer choice. When the smart grid is established, we will have multiple consumer products. We have one-way communication right now, whereas with the smart grid, we will have two-way communication. In normal electric grids, we use a few sensors, but in smart grids, we will be using many or millions of sensors and monitors. Limited transparency in the existing grid. There will be greater transparency for the consumers. Reliability will be higher in smart grids. So with that, with smart grids, so we have to move from smart homes to some smart buildings, smart grid, smart transportation, and then finally a smart city. So this is a vision of the smart city, and Cochin is going to be one of the smart cities of India soon. Let us go through some of the networks also. The first one is the home area network. So this is a dedicated network connecting all the home or office appliances. Okay, so all the home appliances can be connected together by using this HAN. So this is actually a subsystem within the smart grid, and through the home area network, the smart grid will be able to implement the demand side management, or the smart grid will be able to control the devices at home. And using the smart grid, as a consumer, you also will be able to control all your home appliances. So on a later point of time, all the home appliances will be smart appliances. Every home appliance will be connected to the HAN network, whether it is your water heater or refrigerator or television or your car, whatever you think about, everything will be a smart appliance, and you will be able to turn it on and off remotely using the HAN network and the smart grid. This is just a picture of the home area network. So we will skip the slide. So it can be used for effectively monitoring and managing the load. The communication may be wired or wireless. There are different technologies used. Then we come to the neighboring area network. This is also important. This network, that is the neighboring area network infrastructure, this is also part of the smart grid. It allows to connect smart meters and distribution automation equipment to wide area network gateways. So it is actually a wireless community covering a geographical area larger than the home area network. So a larger geographical area community will be connected together. So it may consist of groups of individuals, devices, or buildings with similar communication characteristics. The groups may be bulk generation, transmission, distribution, consumer, utilities, or operations. So all these things, HAN, NAN, and WAN, all these are parts of the smart grid. HAN is a network within a home or office. NAN connects a larger geographical area, and WAN, through WAN we can connect it. WAN means something like internet. We can connect it directly to the utility. So a wide area network, WAN, covers a large geographical area. It is something like an entire city or an entire state. So it spans large geographical area, or you can say it even interconnects lands. So various types are there: point-to-point technology, circuit switch technology, packet switch technology. So these are different technologies available. So this is a wide area network in a picture form. You can see a group of homes connected through a NAN, and each home will be having a HAN, and through the NAN all the smart meters are connected to the data concentrator, and from the data concentrator through the WAN, it can be Wi-Fi, GPRS, FiberNet, or anything. It can be connected to the utility. So from HAN, NAN, through WAN, we will be connected to the utility. So we now move on to the fourth section, which is the Intelligent Electronics Devices, or IEDs. Before moving to IEDs, let us understand what are the data acquired from normal relays and circuit breakers. So you can see this picture where you can see relays connected to a circuit breaker. So these relays basically get real-time values of currents in all the three phases, voltage of all the three buses, then three-phase watts, three-phase wars, then the circuit breaker trip close status and control, then reclosure status and control. So these are the signals which are acquired by the relays for use for controlling the circuit breaker. Now, the remote terminal units are wired to the circuit breaker contacts in the substation switchyard. So a typical RTUs are shown here. So they are wired to the circuit breaker and they are normally situated in the substation switchyards. So data is collected by RTUs located in substations. And RTU also collect data through installed transducers and CTs and PTs, or in general instrument transformers. So all this data is fed to a supervisory control and data acquisition SCADA system. And SCADA will start monitoring and analyzing the signals. But this SCADA faces some drawbacks. Its design is not very robust. There might be errors in the readings because of some malfunction of CB contacts or RTUs. Its scanning rate is very low. It's only 1 to 10 seconds. So any dynamic change occurring in the grid cannot be monitored using a SCADA. So if any dynamic change occurring shorter than 1 second cannot be seen by SCADA systems. So these limitations of SCADA can be overcome by using intelligent electronic devices. So we will see what is an intelligent electronic device. So an intelligent electronic device looks somewhat like this. Of course, the shape vary with company to one manufacturer to another. This is from ABB. Basically, it is a microprocessor-based controller of power system equipment, such as circuit breaker, transformer, and capacitor bank. We can install IEDs at different parts of the power system. Smart grid require the use of a lot of IEDs to manage the balance between the need of the user and the interaction, and for the interaction of the DG equipment with the electrical system. So IEDs, intelligent electronic devices, are installed in substations for automation of data, connection of data, analysis of the data, then improve the integration of data, monitoring, control, and protection. They are very fast. So all these things can be done in fraction of seconds. Data sampling synchronization is the major advantage of IEDs. So IEDs installed in different parts of the power system can be synchronized with time. Right now, it is in the process. So what is the signal at different parts of the power system at a particular time? So that is sampling synchronization. So we collect samples which are synchronized at different parts of the power system. Then if you have this sampled data, it can be correlated between different substations or internally in a substation between different recording instruments. So once you have data which are synchronized with time, it can be used for correlation. So this is a functional architecture of an IED. It can be used for monitoring, metering, protection, control, and the human machine interface allows to change settings, configurations, program it, create different analysis, then record the data are possible by using the HMI. And it also can connect it to the substation server, and through modem it can be connected to remote computers. As an example, a 132.11 kV substation model with a double bus. You can see there are two buses. Arrangement is shown here, and you can see a lot of IEDs installed. IED 1, 2, 3, 4, 5, 6, 7, 8. You can see a total of 12 IEDs are installed. So this will fetch a lot of information synchronized with time. So you can take the samples exactly at a particular time or different times. So the signal, all the signals will be time synchronized. Here we will just see three types of IEDs. One is called the digital, there are many other types also. One is called the Digital Protective Relay, or DPR. So actually DPR is decided from the name itself. It is a digital protection relay. Okay. It can monitor operating conditions like abrupt changes in impedance, current, voltage, power or frequency on a transmission line, and trip circuit breakers when a fault is detected. So remember that these are microprocessor or microcontroller based systems which are very fast. So they can monitor abrupt changes in various parameters and trip the circuit breaker whenever there is a fault. The second one is the DFR, or Digital Fault Recorder. As the name indicates, it can record. Recording is the important part. It can capture and store transient events which are of short durations, and also it can store longer term disturbance and trends of input quantities such as RMS frequency, harmonics, etc. So storing the trend, storing the transient event, this is very important for research and analysis, and make proper improvements later. Then CBM, it is a circuit breaker monitor. So it monitors the circuit breaker's condition online. So these are the okay, this leave this part. This also we can. So basically you can see from the bottom DFRs, DAPRs, CBMs, signals from RTUs, all this will be finally producing a lot of analysis results and reports, which we call DFRA. DFRA is an analysis report which comes from DFR. DPRA, it is an analysis coming from DPR, and so on, CBMA. So these IEDs, data from IEDs can be used for generating a lot of reports, and also making studying and making research on this data and improving the our grid. So applications are developed for processing data, which we have already seen: circuit breaker monitor analysis, digital DPRA, DFRA. So various analysis of the signals are done. All these are done by computer, and they get signal from CBM, DPR, and DFR. Who will use it? This information will be used by operators, engineers, maintenance staff, and also it can be used for research purposes. Now we move on to the fifth section, which is phasor measurement unit and WAMS, wide area measurement systems. So let us start with phasor measurement unit. Phasor measurement units are recording devices, digital data recording devices that can measure and export GPS synchronized high sampling rate dynamic measurements of phase angles, voltages, currents, and frequency. Why it is important, we will see in the coming slides. PMUs will replace the traditional SCADA. So we will make a comparison between SCADA and PMU. These are two standalone PMUs from ABB and Macrodyne. These are integrated PMUs. Integrated PMUs means these PMUs can be integrated with circuit breakers. For example, the phase angle measurement in a power system is very important. Let me put forward a question. What causes power to flow in the grid? Why the power flows in a grid? Let us consider the grid is DC. Why current flows in a grid? Or what causes power to flow in a DC grid? Can anybody answer to this question? I think there are a lot of power system people. What causes power to flow in a DC grid? First start with DC grid. The answer is here. Power flows from a point of high voltage to a point of low voltage in a DC power system. What about AC? In our power system, the voltages are more or less constant everywhere. So there is no point of high voltage and point of low voltage. Then how the power flow in AC? The voltages are same. Any suggestion? Any answer? Yes, I think somebody is ready to answer. Tell me. Okay, now what is there? Power flows from a point of high voltage angle to a point of low voltage angle. So the higher the angle, the greater will be the power flow. So the phase angle measurement is very much important in power systems. And that is why phasor measurement units are getting popular. So if you want to analyze the power flow in an AC system, we should know the voltage angle at different What is a phasor? A phasor is a voltage in current. So phasor is just a rotating vector. A sinusoidal quantity can be represented by a rotating vector or phasor. And a phasor measurement unit, it uses the DFT to obtain the fundamental frequency components of the voltage and current. Let us see this bus 1 and bus 2. One phasor measurement unit is connected at bus 1 and another at bus 2. The blue waveform, sinusoidal waveform, is the voltage signal obtained from the PMU installed at bus 1. And the red sinusoidal wave is the signal obtained from PMU at bus 2. So clearly you can see that the red and the blue, they are not in phase. There is a phase difference. And the dotted sinusoidal wave It is the common reference signals obtained from the GPS. Remember, both the PMUs are connected to the GPS. So GPS can provide a common reference signals. And from this common signal, the blue one is displaced by theta1, angle theta1, and the red one is displaced by a phase of theta2. So by installing PMUs in different parts of the power system and connecting all of them through the GPS, it is possible to find the precise angle difference between the voltages at two different phase points, voltages or currents at two different points of a power system. It may be between one substation and another substation, or it can be, I mean, you can put large number of PMUs all throughout the power system and precisely get the voltage phase angles deviation from the reference signal, and these voltage deviations actually lead to the flow of power. This type of GPS satellite synchronization was not available in normal RTU based SCADA. So we can use a SCADA to make a local control of the substation. We cannot make we cannot control the entire power system by using RTUs and SCADA. So this is a closer view of SCADA and PMUs. SCADA uses analog signals. Measurements are analog, whereas PMUs make digital measurements. The resolution of SCADA is only 2 to 4 samples per second, whereas PMUs up to 100 samples per second. So SCADA, the observability is steady state, whereas PMU, we can use it for transient and dynamic observability. Very minute changes can be observed by using PMUs. SCADA is used for local monitoring, whereas PMUs can be used for wide area monitoring, because PMUs can get the data from different places where it is located. And all PMUs are basically connected to through GPS it is connected to the satellites. So you can get synchronized data, and phase angle measurement is not possible in SCADA system, whereas it is possible in PMUs. This is a picture of a SCADA and a PMU. It is something like viewing an X-ray and an MRI of the grid. So you can see here a small period of time. You can see in the first picture, the voltage is going down and then goes down to some value and then goes up. And that small time, the variation in voltage can be seen very clearly using a PMU, because in a SCADA we get information every second, whereas in a PMU we get data every millisecond. So SCADA data can be used only for static purpose, whereas here a PMU data, we can get a complete dynamic or transient information of the variations. So it is compared to X-ray and MRI. So here you can see the time between 5:21 and 5:22. You can capture using a PMU data, second picture. Whereas this small time 5:21 to 5:22, you cannot capture it properly using a SCADA. So this is a real-time SCADA data from Kramer substation in California, and the same data using a PMU, you can see that within 1 second, what all changes are happening, how the voltages are changing within a short span of time. So you can see the comment on the right side, it's like going from an X-ray to an MRI of the grid. This comment was first told by Terry Boston, CEO of this Kramer substation. So with the data measured from PMUs, we can make a thorough analysis or dynamic analysis, dynamic study of the power system. If you see here, this picture, SCADA measurements cannot see most oscillations. So minute oscillations which happens within a second or within milliseconds, SCADA cannot even measure. And worse, they can give misleading impression also. Whereas data from PMUs, we call it synchrophases. Synchrophases are needed to observe oscillations because of faster data sampling, greater data resolution, and wide area. So wide area is not possible with SCADA, only local. SCADA is used only locally. So faster sampling, greater resolution, and wide area, 3 advantages of using PMU. This is the block diagram of a phasor measurement unit. We will see one by one all of them. First, you can see the analog inputs coming from the power system. These analog inputs can be voltages, currents, etc., coming from CTs, PTs. It can be P, Q, and all. It goes through an anti-aliasing filter, then A to D converter. There is a phase locked oscillator, and there's a microprocessor, and then the modem to communicate with the outside world. You can see a GPS receiver connecting to a set of satellites, not just one satellites. We will see why we need a lot of satellites in the coming slides. So the voltages and currents in the analog form are derived from PTs and CT secondaries, and it goes through an anti-aliasing filter. We need an anti-aliasing filter to restrict the bandwidth of the signal to satisfy the Nyquist-Shannon sampling theorem for the fixed sampling frequency. Then GPS, it provides accurate information about the location and time of the GPS receiver's location. So, two things. One is the location and the time. When you take a signal, from which location you got the signal and at what time you got the signal. So every signal is location stamped and time stamped. And all the PMUs are time synchronized. They work with the same clock. So it consists of 24 satellites. It's a network of 24 satellites. And these 24 satellites are orbiting in 6 geosynchronous orbits in such a way that at a given instant, 4 satellites are visible from any point of the Earth's surface. That is why we are going for 24 satellites, a network of 24 satellites. Any point on the Earth will be visible to at least 4 satellites at any instant of time. And these satellites are capable of transmitting common access 1 pulse per second with an identifier, which is accurate about 1 microsecond at any location on Earth. And this pulse combined with the time tag is crucial for the application. phase-locked oscillator, pulse signals from the satellites are phase-locked with the sampling clock. So we will skip this part. Using the synchronized clock as a reference, a PMU creates a phasor representation of a constant sinusoidal signal. So all the PMUs in a power system use the same time reference. So what will happen? The phase angle differences between the phasors coming from different PMUs will be very accurate. This is not possible with our traditional RTUs and SCADA. So we can get precise information about the phase angle of voltages at different parts of the power system very accurately. Then comes the A to D converter. I think all of you understand what is an A to D converter. Converts analog signal to digital signals. This is a conceptual diagram of a power system with PMUs. You can see this is the entire power system with PMUs connected at different places. All of them are connected to the satellites, and there is a control signal which will receive signals from all different locations. So we get large number of signals, and these signals can be analyzed and utilized properly. So the advantage of PMUs are more number of samples, 25 to 100 phasors in every seconds. They are time synchronized and also location stamped. So every signal will be stamped for location and time. We get a finer view of the electrical system. We can develop adaptive protection systems by studying the data. And by recording all this data, because we have a lot of data, we can analyze any post-disturbance with more accuracy, which will help us to plan such contingencies in future. And there are many more advantages also. So some applications are listed here: oscillation detection, fault location, fault classification, event analysis, model validation, situational awareness. So if you can get PMU data from 2 different PMUs, there is enough information to do a 10 PhDs. So a lot of power system analysis can be done by extracting the signals from various PMUs. Let us go through the wide area measurement system, WAMS. It's a collective technology to monitor power system dynamics in real time, identify system stability related weakness, and help to design and implement countermeasures. This is the IEEE definition. Wide area measurement is based on PMUs. Because the data, PMU data, is precisely time synchronized. We get time synchronized values of voltage and current phases. And also we get the frequency, rate of change of frequency, breaker position, etc. So by employing a lot of PMUs at different parts of our power system, or at least every substation, if we have 1 or 2 PMUs, we will get a complete idea about the whole power system. So the signals from the PMUs normally go to a data concentrator, and from the data concentrator it will go to a super data concentrator, where basically it's a computer where all analysis can be done. So the components of WAMS: PMUs, data concentrator, GPS for time synchronization, then communication channels, and all this will fetch a lot of information which can be analyzed using different software tools. There are analysis tools and awareness, situational awareness system, then wide area protection and control systems. The speciality of WAMs is that all these PMUs have a common reference signals, even though they are located at remote locations, and they are synchronized using GPS. So the data is synchronized, time stamped, location stamped, and all of them have a common reference signal. We can use an absolute time reference across the power system, which was not possible before. So PMUs enable us to use an absolute time reference across the power system. So at one point, you can make the reference phase angle 0 and compare the signal at other parts, whether it is leading and lagging, and you can analyze the power flow within the power system. So we are approaching the last session, which is the 6th session. I wish to take a 5 minutes break for a cup of water. Can I take a break, miss?
Okay, sir, sure.
Okay, thank you very much. Okay, I'm back. Can I continue, ma'am?
Yes, sir. Welcome.
Yes, sir. Yes, sir.
Okay. So we are now going to our last session, which is the smart substations. So substation is a part of an electric generation, transmission, distribution network. We all know substations. A substation transforms voltage from high to low or the reverse or perform any of the several other important functions. So what are the several other important functions? We will see one by one. So we need a substation for practical consideration to satisfy load growth, accommodate new generation, maintain reliability, and technically to step up and step down voltages, break the power flow, provide support to the power flow. These are the different components of a traditional substation. You will see transformers, switches, circuit breakers, CTs, lightning arresters. These are the traditional substation parts. This is a typical distribution substation, a well-arranged one. You can see the fencing, lightning arresters, and all those step-down transformers, incoming lines, outgoing lines, circuit breakers, distribution bus. There are different types of substations. One is a transformer substation, so which a transformer substation change the voltage levels from high to low or low to high. Then there are some substations which are switching substations. So they do the switching operation of power lines. There are some power stations for power factor correction, PF correction substations. We employ synchronous condensers as power factor improvement equipment. Then frequency changer substations. So these are normally used for industrial utilization. Some industries work, some equipment work at a different frequency. So we need to change the frequencies. Then converting substations. So convert AC to DC by using power electronic components like SCRs or other devices. This is very much essential for railways used for traction, because in traction mostly they use DC. So the AC has to be converted into DC. So you will see these substations along your railway lines, the railway tracks. So moving to smart substation, how can we make a substation smart is a normal substation plus the latest information technologies. So if we make use of the latest information technologies, we will have a substation. See, latest information technologies even allow to have unmanned substations now. So that we have modern substation very near to us, which is in Tripunithara. One digital unmanned substation is there. So even for only rarely people go there for some maintenance, otherwise it's unmanned, completely automated substations. So basically it focuses on secondary devices, protective relays, CT, PT, and all this will be microcontroller driven or microcontroller based, and in general we call it intelligent electronic devices. Instead of serial communication, we will be using Ethernet switches and TCP public IP. We will be using an application for protocol IEC 61850. This is a special application protocol used in substations. Substation application have to utilize real-time information. Then artificial intelligence techniques will be used for making fast decisions. So if we go for micro-based or microcontroller-based, microprocessor-based or microcontroller-based relays or other intelligent devices, it gives us a lot of flexibility and functionality. So we will be having low-cost monitoring analysis, and we can better diagnose electrical faults. This picture shows the evolution of the protection system. This is just for you to understand how we evolved over years. You should start from the right, 1, 2, 3, 4. Initially, we had non-microprocessor relays in one. If you see one, we had relays which are not operated by microprocessors. Then RTU came. Then later, IEDs hardwired with process units came, which used Goose. This is a generic object-oriented substation event. This is a specific standard used in substations. Then later came the fourth block. Many units got merged, and IEDs also sometimes merged with either the protective devices or the control devices, and IEC standard 61850 got implemented. So this is basically an evolution of the protection system. So the protection system has gone a lot of changes from analog to digital, and the communication also from hardwired to wireless. So even the transformer, instrument transformers and normal transformers, you will not find transformers with windings. Telco already started building transformers without any windings. It will be power electronic transformers. So a smart substation, this is an overview of a smart substation. What you see at the rectangle in the bottom is the substation. So inside the substation, there will be a substation LAN where all the IEDs, intelligent electronic devices, protective relays, and the substation server will be connected to the substation LAN. There is a video surveillance server separately, which will be connected to the cameras fitted all over the substation premises. Then the substation LAN is connected through a network switch and router, and through firewalls, various firewalls. These firewalls are very important because we are now going to connect a substation to the exterior world, and this means there can be cyber attacks, and there might be, if somebody can break these firewalls, then they can attack our substations and they can bring them down. So the entire grid can be brought down. So you can see through the firewall, it is connected to corporate LAN, DMZ LAN. DMZ stand for demilitarized LAN, control LAN, physical security LAN. DMZ LAN is important because it is going to connect with the external world. Other thing, control LAN, physical security LAN, all this is part of our power system only. Corporate LAN, this is for connecting to the market and other things. Whereas DMZ LAN connects the substation LAN to the to external people through the internet. So this LAN is something very very difficult, or this firewall is very difficult to be broken. And from here we move to what is IEC 61850. It's a global standard for communication in substations. It enables integration of all protection, control, measurement, and monitoring functions within a substation. So a substation is basically divided into 3 levels or layers. One is the process level, bay level, and the station level. So you will find CTs, VTs, transducers, circuit breakers in the process level. So the function of the process level is the line protection, control, disturbance, recording, data acquisition, etc. If you move to the bay level, you will find IEDs for protection control. So the process level disturbance, recording, issuing comments, etc. will be done at the bay level. And if you move to the station level, you will find operating computers, operating station, engineering station, then the gateway to the outside world. So at this station level, evaluation of the disturbance recorded at the bay level will be done. Busbar protection, automatic sequencing, station-wide interlocking, archiving system supervision, and time synchronization. Yes, that is a very important part. And a gateway for remote communication. All this is done at the station level. So this is another picture of the same information. So 61850 smart substation architecture divides substation into 3 levels. Process level at the bottom, which takes care of all the signal measuring, transducers, and signal processing. Bay level, here some analysis and recording. Recording is done, not analysis. And it issues comments to the process level. At station level, evaluation and interlocking, time synchronization, etc. is done. So it is again detailed here. At the process level, all the switchyard devices which are hardwired using copper cable comes under this process level. So CBs, isolators, earth switches, instrument transformers, etc. And use fiber optic cables to connect the bay level IEDs. So in the bay level, there are IEDs. The connection between the bay level and the process level is through optic fibers. So at the bay level, the IEDs provide all bay level functions such as control, monitoring, protection. These IEDs are directly connected to the switchgear and they don't need additional transducers. At this level, each IED is independent of the others and its function is not affected by any fault occurring in any other bay control unit of the substation. So if any bay control unit is faulty, it will not affect another IED at the bay level. And the station level, you will find a redundant PC-based HMI, human machine interface. So it will enable the local station control through a dedicated software which contains extensive range of SCADA functions. And here you do a lot of analysis which cannot be done at the bay level. It produces alarm listing and also it produces event list related to the entire substation, and also it is a gateway for communication to the outside world or to remote control stations. And you will also find a master clock, a dedicated master clock, synchronized globally. There are some other equipments also. We will skip this for the time being because you can just read and understand it. So the features of IEC 61850 is interoperability. The configuration, freely configure any possible number of substation protection and control functions within one or two IEDs. You can keep adding on IEDs. It's very modular construction, very simple architecture, and overall cost saving. So the communication is within the smart substation is done by IEDs using SMV, MMS, and GOOS. GOOS stands for Generic Object Oriented Substation Event. So these are not of much interest for us. So let us. So here this is a comparison of substation, again substation evolution. You can go through it and you can see that our electrical substation has evolved, how it has evolved over years. From conventional substation, we moved to digital substation, and now we have smart substation. And you can see the next generation substation where many units will be merged, and everything is modular and layered, well connected with high security and all. So this is another picture showing the protection system in a smart grid. You can see A, B, C, D, 4 substations. Each substation has its own protection and security, and all of them, SP stands for substation area protection, and from there it is connected to the wide area protection. And within the substation, every unit has a protection. UP stands for unit protection, SP stands for substation area protection, and WP stands for wide area protection. So these are different protection layers. There are different types of substation, and we will see the automation and various architectures: simple cascading type, redundant cascading type. So simple cascading type, you will see HMI, the personal computer, or which is an industry personal computer, IPC, and lot of Ethernet switches connected to the RCUs or BCUs. So BCU means a bay control unit. So this is a simple cascading type. If you go for the next, you will find redundant cascading type, where you will see Ethernet switches on both sides of the bay control units. So these are different architectures. Each architecture has its own advantage and disadvantage. So this is a ring type of architecture. So you can see Ethernet switches on one side, but they are connected as a ring. Then this is a star type of architecture. You can see one Ethernet switch connected to all other Ethernet switches, and then connected to the bay control units in the substation. Then a hybrid architecture. So hybrid means a combination of both. And these are some of the references which I have used. I have used large number of references from the internet. And with that, I think 11:41, it's time to wind up. So we will have an interaction section. If there are questions, we will continue. Thank you very much. Thank you very much, Sito Miss, and thank you for giving me an opportunity. I thank the management, the staff attending the seminar, for patiently listening to me. Thank you very much.
Thank you, sir. Thank you. Thank you for such a wonderful section, sir. And you have filled our brain with more ideas, sir.
Thank you. Thank you very much, ma'am. So if there are one or two questions, I will be happy. Otherwise, we will wind up the session. One thing I want to tell you is this FDP is a surface treatment of the subject, because with a heterogeneous group of people, I cannot go into the depth of each and everything. So those who are interested, this will be a starting point to do further research. Thank you. Thank you very much.
Yes, sir. Sure.
So shall we wind up, Miss?
Yes, sir. Once again, I thank you, sir, for accepting my invitation in spite of your busy schedule, sir.
Okay. Thank you very much. I will log out. Thank you. Thank you all staff. Thank you the management
Thank
staff
you,
of
sir.
committee. Thank you very much. Thank you. Bye.
And thank you, participants, for your live participation.